Yeah. The pointer is just in the back.
On the back. Okay.
Yeah.
And that's the
Just
advance.
yeah.
Okay. Good. 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 Good.
Ok, pessoal, vamos começar? Então, hoje vai ser o dia todo apresentações do SGS, né, até o final da tarde. Se a gente tiver um tempinho, como eu falei ontem, a gente apresenta a parte final do laboratório e a parte de monitoramento por satélite, senão só na quinta-feira de manhã. Por favor, Mônica.
Bom dia a todos. Okay, I thought it was very valuable yesterday to hear Walson talk about the networks here. So I wanted to talk a little bit about the USGS monitoring network and some of our major initiatives and focuses in our agency and how that might be the same in some ways as ANA and CPRM and in some ways different. So I introduced myself yesterday. Again, I'm Molly Wood. My title is the National Sediment Specialist for the USGS's Water Mission Area. And my background is in civil and environmental engineering. I'm also a hydrologist. I've been with the USGS for about 17, 18 years. I physically live in Boise, Idaho, which is this star right here, so kind of the northwest part of the United States. And these are some pictures from where I live. The climate is somewhat similar to here in that it's dry and we don't get very much rain throughout the year. Low foothills, some forests and mountains, but a lot of rivers and a lot of, I wouldn't say a lot of sediment transport, but we do get sediment transport and it has some pretty pristine river systems in Idaho, so it's a nice place to work. So before I start on the USGS network, I'm gonna give you a quiz. So this is a picture of a river in the southwestern United States in New Mexico. This is a site that has very, very high sediment concentrations, and it has made sampling very difficult because of the high concentrations. And so I'm going to ask you this question, and then I want you to give your best guess, but then we're going to come back to that question at the end and see if you got it right. So the question is, how much sediment do you think is passing this site every hour? Is it 90 tons, 600 tons, 3,000 tons, or 23,000 tons? So every hour. So just mentally make a note of what you think is the loading at this site. Okay, we'll come back to that. So why do we monitor sediment in the U.S.? Most of the sediment monitoring that we do as USGS is associated with a very specific problem that another agency has, and they come to us and they ask us to do sediment monitoring to answer this specific question. That's most of the monitoring that we do. And so a lot of the drivers or purposes of our sediment monitoring program, they're very varied. And sediment is an interesting thing. We don't always think of it as a pollutant, something that pollutes our waterways. And it's some level of it is required for maintaining the natural ecological health of a system, natural stream formation and river formation. But if we get too high of a level, then we can often impair biological habitat for aquatic organisms, fish, things like that, impair water quality. We can affect flood protection of our infrastructure, decrease reservoir storage. It can impair waterway navigation, and it can also transport other pollutants that tend to be associated with sediment, things like metals and nutrients and things like that. On the other side, too little sediment can also cause problems. We can lose agricultural land. We can use land that's used along our coasts, things like that, if we don't have enough sediment delivery to those systems. So understanding the amount of sediment can be very important for answering a lot of these science questions. So these are the common types of problems that we will have in the U.S. that there's a need for monitoring sediment to address. So also, sediment can cause a lot of damage. It's been estimated that sediment-related impairments in North America total over $20 billion annually. And so it's a common problem. I'd say the most of this damage is associated with the loss of storage in our reservoirs, so infilling of our reservoirs. So in the U.S., we work very closely with other federal agencies, other state agencies, and our partners in the federal government, two of them, mainly the U.S. Army Corps of Engineers and the U.S. Bureau of Reclamation. Those are two federal agencies that we work very closely with on sediment-related problems. They maintain a record of reservoirs across the U.S. that are, and the rate at which they are infilling and the rate at which they are losing their capacity to store water. And this is a graph showing the, so every time that they do a survey of the capacity of a reservoir, they document that, and then when they come back and do another one, they'll document the change. And so they maintain a record of that, and they keep track of the top reservoirs in the U.S. that are losing their volume the quickest. So these are the top 10 reservoirs that have lost capacity or lost volume in recent years. And this top one, Bonnie, has lost almost 27% of its total volume to infilling by sediment. So this is really a big concern. The sustainability of these reservoirs over time is a big concern, and so often these agencies will come to us and say, we really want to know what is the sediment budget for this reservoir, how long is it going to last, do we need to do something to remove the sediments that's there so that we can use it for a long time. So that's a common question that we get associated with our sediment monitoring. This is an example of a dam in California, and this is a dam that was built in 1947, and it's about, when it was built, it was the height of the dam was 60 meters, and it's been the subject of a lot of sediment filling in over the years, and this is how much the sediment has filled in. This is behind the dam. Sediment has come in and filled to within about 4 meters of the top of the dam. And half of that, let's see, I think I have a line. Yeah, so this is the approximate sediment level here. Half of that sediment came from sediment loading from one wildfire. This is a watershed that has a lot of wildfires, and so there's a lot of sediment runoff from that landscape. And so this is a big concern, and trying to understand and predict these kinds of sediment loads and how much it's going to affect a reservoir is a very common issue for us. So in response to all those problems, we have a pretty large monitoring network. This is a picture of the locations where we monitor sediment across the nation. The blue circles are sites where we collect sediment samples. We call this discrete data. The red circles are sites where we collect samples, but we also generate daily estimates of suspended sediment concentration. So in total, on average, so the number of stations that we operate varies a lot because we often have these other agencies paying us to collect the information. And so their needs vary from year to year. And so I would say on average, and I was wrong about this number that I told you yesterday, Walson. So on average, we collect sediment data at about anywhere from 1,000 to 1,500 sites across the nation per year. And then for daily sites, I think on average, it's anywhere from 70 to 130, 140 stations each year where we produce daily estimates of suspended sediment concentration. So yeah, again, that varies from year to year, but that's kind of the number that is typical for us. Yes?
I have a question.
Yeah. Let me turn on my...
No slide anterior, por favor. Na verdade, os pontos azuis que você falou são dados discretos, né, de concentração de sedimento de suspensão, né, granulometria, e os vermelhos são... vocês geram dados diários, mas a coleta de amostras é com uma frequência diferente ou é só o processamento de dados que vocês geram aquela descarga sólida diária, mas a coleta de amostras é, sei lá, a cada mês, a cada 2 meses, a cada 15 dias, não sei. Queria que você explicasse um pouco mais isso, que eu não entendi bem qual a diferença dos pontos azuis para os pontos vermelhos.
Yeah, so it varies per site. At some sites, we have what's called an observer, so someone at the site that collects a sample every day. But at some sites, we have a rating curve, like you do, between sediment and flow, and we just collect samples periodically, maybe the same frequency as we do at the discrete sites, and then we just generate a daily record based on that rating. At some sites, we have a surrogate relation, which I'll talk more about, and we use the surrogate information to generate a daily record. But in general, yeah, so it varies, but the frequency of sampling can be the same as a regular discrete site. A typical frequency every 6 weeks is typical. We try to time our samples to be about 80% of our samples are timed with hydrology, so capturing variation over storm events, and then 20% may be at a regular interval, like every month, every other month, that kind of thing. Yeah.
As nossas estações não têm a curva-chave de sedimento. Vazão, sedimento. Como você falou que a sua lá tem. Correto, Walson?
Ela comentou. Uma pergunta ou algum comentário?
Não, ela tinha comentado que a nossa tinha.
Não, não.
Não?
Falou que o deles tem.
Então.
Não.
Como a nossa.
Não. No, please go.
Inanna, is he saying at...
Não, é porque o Pedro só confundiu, é porque no final da minha apresentação ontem, eu mostrei, enfim, só a título de ilustração, alguns trabalhos que podem ser realizados utilizando os dados sedimetométricos, e para aqueles trabalhos nós traçamos curvas-chave de sedimento. O que a Molly está dizendo é que eles fazem isso para gerar a descarga sólida diária para várias estações deles. Foi só isso que ela falou.
And we'll talk more. I think Tim is talking later, maybe Thursday, about the ways that we compute sediment loads and the different kinds of rating curves and approaches that we use for generating daily and hourly records of sediment. Okay, so the next few graphs I'm going to show you are showing kind of the types of samples that we generally collect. And this is divided by decades since we've been collecting sediment data. And the graphs I'll show you go through the last full decade, 2000 through 2009. We are currently working on a compilation for the current decade, so I don't have those numbers to show on the graph. So, but this will show you the trend that we followed in USGS for sediment monitoring over the past century. So this is a graph showing the number of samples on the y-axis versus decade that have been stored in our system and that have been documented for concentration, which is the dark graph, the dark bar, the percent of samples that have information about the percent of sand versus silt in the gray bar, and then this small, the white bar is the number of samples where we have documented the actual sampling method that was used. And so a few patterns here that I'll show is the number of samples that we've collected and documented for suspended sediment concentration kind of peaked in the 1970s. And this occurred, there was a large USGS project during that century related to understanding coal hydrology. And that kind of started up in the 1970s. Prior to that, most of the sediment monitoring was done related to irrigation, evaluation of sediment loading from agricultural lands and irrigation, effects of irrigation practices. And then in recent decades, after this program in particular was ended, most of the sediment sampling that has been done has been associated with individual projects that USGS has operated in response to a particular agency need, and also some national programs. We have a national water quality monitoring network and some national sediment networks that were implemented during that period. So that's, we did see a decline after the 70s, but still, we're still about at this level at this point. So another thing that I will say is, unfortunately, we don't always collect sand and silt fractions with every sample. And I wish that we did. I wish that we had the money to do that for every sample, because that's very valuable information to have with every sediment sample. But we've done a much better job in recent decades of documenting more information about the types of methods that are used for our samples and the types of samplers and equipment that we use. So we're doing a much better job of that in recent decades. This is the same kind of graph, except this is showing you the number of sites that have been sampled for suspended sediment concentration in the dark bar. This is the number of sites with more than 10 samples during that decade. And again, we had a peak in the 1970s associated with that coal hydrology project. And then we've been declining since then, but we're pretty close to this at this point, maybe a little bit more. And then the lighter bar are the sites where we're actually computing daily records. So much lower than the number of sites, the discrete sites, but we still do that at a lot of sites, the daily records. And then you'll notice one thing that's been a trend in recent years is this is the number of turbidity sites. So the sites where we're measuring turbidity, and in many cases using turbidity to estimate suspended sediment concentration. That has grown in recent years, and this number is even greater in the current decade. So that's been a trend that has grown, certainly as instrumentation has advanced and we start thinking about surrogate technologies, which I'll touch on briefly in a minute. So these are the sampling method types. So this is the number of suspended sediment samples on the y-axis versus the different sampling methods that we use here. So the tallest bar is the equal width increment method. So by far that's the method that we use the most. And then equal discharge increment is smaller, but I think we're using this more and more. So with the current compilation, we'll probably see that this bar has increased compared to the equal width increment. I'll mention some of these other methods in a minute, or actually later today when I talk about suspended sediment sampling. So our priorities in our program, I'm going to touch on 3 priorities or focuses that we have. Number 1 is consistency and quality. And we are striving to ensure that we collect the best sediment data possible using tested and consistent techniques across all of our offices. Another thing that we consider a priority is the development of innovative or new techniques. So we want to develop new and efficient monitoring techniques that expand the amount of sediment data that we make available to us as an agency and to our partner agencies. And then we also want to provide a lot of technical support. So Tim and Mike and I answer a lot of questions to USGS for USGS personnel on methods questions that they have, and we want to help them, and we want to help them and our partner agencies understand the methods and promote growth in our networks and advancement in our the quality of our sediment data and research. So Tim will talk more about the Federal Interagency Sedimentation Project, or FISP. So this is a very important part of our priority to promote consistency and quality. So the FISP was developed in 1939 to standardize and unify sediment data collection across all of the U.S. government agencies that were collecting sediment data. And it was primarily focused, it has been primarily focused on developing samplers. So all the samplers that we talk about were developed and promoted by the FISP and tested by the FISP, and also new monitoring technologies, new approaches for measuring sediment is also a focus of the FISP. And so we all talk about FISP approved samplers. Tim will talk more about those later. And then, the FISP chief right now is Tim Straub, so you'll get more information from him on this program. So we have a website, and it's linked here. And another piece of our mission to promote consistency and quality is to develop policies and standards and methods that we publish and make available to everyone. And Wallace talked about this, that everything that we do, we try to publish that method so that it's accessible to everyone to follow or to comment on if they want. And so on our website, we maintain a list of policies that document what we can and can't do related to sediment data collection. And it's hard to see, but this is sort of the start of the list here. And then we also provide access to our technical publications. So one of the key report series that we publish is called Techniques and Methods. And that documents standard ways that we do things. And so someone could pick that report up and follow those procedures step by step and implement that for their own programs. Related to that, many of you know about the sediment compilation document we submitted as part of our agreement with ANA and CPRM last year. And this is sort of a summary of all of the key sediment publications in different categories. And Walson talked about this yesterday. He showed you some of the major that you all had downloaded a lot of those resources and made them available. So this document, if you should have access to this. If not, let us know. It gives you links to all of those major resources that we feel like are the most important ones to follow for our sediment data collection practices. So in recent years, our partner agencies have been wanting more sediment data at a higher time resolution. So they want hourly sediment estimates or sediment estimates every 15 minutes, things like that. But they want that information to be better quality, they want it to be cheaper, and they want it now. They want it in real time. And so that's difficult with sediment sampling. Sediment sampling is time intensive. It takes a long time to collect a sample. It's hard to get personnel and staff out there on the river sometimes, especially in high flow situations where it can be dangerous. And so collecting a sample every time sediment data are needed is very difficult and it's very expensive, as you all know. So we've started looking at other approaches for getting sediment estimates when we can't collect a sample. So I'm going to talk a little bit about an example where we started thinking about the need for collecting sediment data more frequently. This is an example in near Atlanta, Georgia, called the Yellow River. This was a storm event in 2009, and the flow, the discharge, is shown in the blue line here. And this is over, about 5-6 days. And there were sediment samples collected, so full EWI or EDI cross-section samples. They were collected about once per day over that event. And for us, and probably for you, you would say, oh, that's a lot of samples. Daily samples over an event is something that we don't always get. So it's really nice to have that kind of information to see what was happening. So yeah, those are full cross-section EWI samples. And the max that was sampled during that event was 250 milligrams per liter among those EWI samples. So another thing that they had at this site was an auto sampler, a pumped sampler. How many of you are familiar with an auto sampler or a pumped sampler or have ever used one? Anyone? No, it's not common. Yeah. So this is it's like a barrel that sits on the stream bank, and it has a tube that goes out to an intake in the stream or the river, and the sampler has a pump in it, and it pumps samples from the river into the box, and there's a series of sample bottles within the auto sampler. So it can collect samples while you're not there during a storm event. It can be activated based on flow at the site or water level or any number of measurements at the site. So they had one of these instruments at the site, and it collected data continuously during that storm event. Okay, so these are all of the samples that were collected using that pumped sampler. And these samples, we were corrected to the cross-section using an approach that I'll talk about later called development of a box coefficient. So we relate the full cross-section sample to a sample that's pumped from the sampler, and we develop a rating, a relationship between those two. So at this site, they had done that over a range of conditions, and they corrected the auto sampler data to what a full cross-section sample would be. So we'll talk more about that later, but just to know that these are the data, these are the samples that were collected during that event. So some things that you can see here is that the auto sampler data gave you much more information about what was truly going on during that storm event than we would have seen with the cross-section samples alone. So we often see that at many sites we see that sediment concentrations will peak on the rising limb of the hydrograph, and then they'll quickly drop off. And then so there's not a very clear pattern with flow, and there certainly is what we call hysteresis or changes or differences in the sediment response on the rising limb and the falling limb of the hydrograph. So if we had not had an auto sampler here, we would not have seen that the true concentrations during that event were closer to about 650 milligrams per liter at the peak. So we did not get that information with just the cross-section samples alone. So as you can imagine, it's expensive to collect a lot of samples using an auto sampler because you have to analyze each one. So we thought, well, are there other things that we could measure that we could put in the river that are directly relatable to sediment concentration, but that are maybe more easy to measure, and that maybe aren't as expensive to use as collecting a lot of auto samples. And so out of that came the concept of these innovative techniques called surrogates. And this is a big focus for us in the USGS, is using surrogate technologies. So I'm just going to briefly talk about some of the ones that we use. So for suspended sediment, some of the most common surrogate techniques that we employ are installing acoustic velocity meters that are mounted in a fixed location, mounted horizontally in the river. And those instruments send out sound waves into the water, and those sound waves bounce off of sediment in the water, and the instrument listens to the reflection of those sound waves, and the stronger the reflection can be related to more sediment in the river. So that's one technique that we use. Turbidity is another common technique that you all are familiar with. There are some laser diffraction instruments that can be mounted in the water that we can use to estimate suspended sediment concentration and grain size distribution. And then another technique that we use at sites that have really high concentration is called a pressure difference, where we install two pressure transducers or water pressure monitors at a fixed distance from each other, and we record the difference in pressure between those two and relate that to the amount of suspended sediment concentration. For bed load, we have worked with our partner agencies and have done some different types of tests. Hydrophone is one, and this is like an underwater microphone that listens to sediment particles bouncing against one another. Impact plates, which is something that you install in a river, and it records the sounds of sediment like hitting that plate along the bed, and that's another technique. And then also tracer materials, either dyed sediment particles or sediment particles that have little radio transmitters in them, and we document the movement of those particles and relate that to bed load. So these are some of the techniques that we are using and testing in the US. So back to this example of the Yellow River. So at this site, they had deployed two surrogate instruments at the site. They had an acoustic velocity meter here, and they also had a turbidity probe. And they looked at the data that were recorded from those instruments during that storm event. In the top graph, the purple line is showing the response, the backscatter response during that event, with the sediment samples still shown here. And then the bottom graph is showing the turbidity response over that event, and again with the sediment samples shown. So what you can see is that these two instruments sort of followed a shape in the response very similar to the actual sample concentrations. So this shows us that these could probably be more directly related to sediment concentrations and used to estimate sediment and they would probably give us a better relation than just using flow. If you could remember, the flow hydrograph did not very closely match the patterns that we saw in concentration from the samples. So we're starting to use these kinds of techniques more and more to give us sediment estimates at a much smaller time scale. So every 15 minutes, every hour is very common for us to try to generate a sediment estimate. So these are some of the sites where we are making surrogate instrument measurements, and we're using them in a lot of cases to estimate records of suspended sediment. We're using these surrogate technologies, as I said, to estimate sediment, but we're also using them to estimate things that are associated with sediment, things like nutrients, nitrogen or phosphorus in particular, bacteria, and some other water quality parameters like metals and things like that. Another thing that we're starting to do more of in the US is called sediment fingerprinting. And as you can imagine, a lot of our partner agencies, when they want us to monitor sediment and develop, say, a sediment budget, that they want to better understand where sediment is coming from so that they can try to target that source potentially and control sediment maybe closer at the source. It may be more cost effective to manage sediment where it's coming from than it is to try to remove it or control it far down in the watershed where that may be more expensive and difficult. So sediment fingerprinting involves, if you have a watershed, identifying the possible sources of sediment within that watershed, visiting each of those sources and collecting a sample. So if I think in this watershed that some potential sources of sediment might be from the stream banks, erosion from the stream banks, runoff from agricultural lands, runoff from dirt roads and construction areas, and also construction over here, areas that may have been subjected to wildfire burned areas, and then there may be some key geologic features that need to be sampled as well. So we would go to each of those possible sources, collect a sample, and analyze it for certain signatures, things like certain chemicals, isotopes, radionuclides, things like that, that would be specific to that source. Once we do that, we collect data in the river near the outlet of that watershed, and we analyze those samples for all of those properties that we analyzed in the samples here. And using some computations that we've developed, you can determine how much of the sediment moving out of the watershed can be associated with each of these possible sources based on those fingerprints or those signatures. So this is an example of a site where that was done, and at each of these rivers they determined what percentage of the sediment leaving the watershed was coming from some different land uses. So I'll touch on this one in particular. This is a river called the Mill Stream Branch, and they found that 100% of the sediment leaving this watershed was coming from erosion of the stream banks itself. So if you were trying to determine how to manage sediment in this watershed and you paid a lot of money to try to control runoff from agricultural lands, you would be completely missing the major sediment source here. So this really helps, and in the US really helps direct money and resources to controlling sediment where it's really coming from. So this is becoming a more and more popular technique for us in the US. So for technical support, we provide a lot of support for implementing some of these innovative techniques that I talk about and helping people do this in their offices. But we also teach a lot of training courses. We teach a number of week-long courses similar to some of the content that we'll talk about this week. We have a week-long class specifically on sediment data collection. We have another one on using large samplers like the D99 on large rivers and some of the special considerations that need to be followed for that. And Mike will talk more about that later. We have a class on analyzing the geomorphology of a river. We have a class on using surrogates, using acoustic Doppler velocity meters to estimate sediment. And we have an in-person class and an online course that you can take at any time that gives you an overview of this concept. We also have one on how we compute sediment records. And then, of course, we offer a lot of webinars, workshops, international classes, that kind of thing. Okay, so back to the sediment quiz. So, all right, so how much sediment do you think is passing this site every hour? See, how many people think it was 90 tons? How many people think it was 600 tons? How many people think it was 3,000 tons? How many people think it was 23,000 tons? You guys are good. The answer was C, 3,000 tons. Yeah, nice job. So this is a site in, it's the Rio Puerco, the Pork River, I think is the name of that. So in New Mexico. And the concentrations are so high that it just makes surrogate technologies difficult. Sometimes it makes sampling difficult. It's really thick stuff. And the phrase has been used that it's too thin to plow and too thick to drink. So it's really, really thick. So the concentrations at this particular point in time were about 47,000 milligrams per liter. But this site has seen concentrations up to about 400,000 milligrams per liter. So really high concentrations. And so one of the techniques that they have used at this site is called the pressure difference method. And they install 2 pressure transducers at a known offset in the river here. And it measures the density difference between the pressure difference between those 2. And then that is related to the sediment concentration in the river. And it's worked really well. It has been tested at several locations in this area. It's very low cost for us. It's about $5,000 for the complete system. But it requires concentrations greater than about 20 milligrams per liter. And really works best with fine sediment loads. So this would be, I mean, in the case in this country, this might be a thought for, you know, a really high sediment loading associated with a dam failure or something like that might be an approach. But typically, I'm guessing you don't see concentrations this high unless there's a major problem. But this is an approach. So this is showing you how well this surrogate worked here. So the blue line is the discharge or flow during a particular event. The black is the estimated suspended sediment concentration using this technique. And they did collect samples throughout the event, and those are the red squares. And you can see that the samples very closely matched the pressure, the estimated concentration using that pressure difference method. So in summary, we're actively supporting and promoting sediment monitoring across all of our stations and networks in the US. We're promoting new ways of trying to get more sediment data more cheaply, quicker, more efficiently. And we're dealing with that in challenging environments, and we're providing that information at higher temporal and spatial resolution than we have previously thought were possible. So we're trying to do that at our networks and provide support for that. So, any questions?
Molly, tem só duas perguntas. Você mostrou um slide bem interessante, aquele artigo, né, eu não conhecia, que faz esse quantitativo pelo método utilizado lá nos Estados Unidos, né? Método de armazenamento de largura, método de armazenamento de descarga, de largura bem maior, como aqui no Brasil. Lá é mostrado também que, em algumas situações, você usa uma única vertical. Tem algumas medições ali. Uma single vertical. Eu queria que você explicasse um pouco mais isso. É o que? Uma amostragem automática? A equipe vai lá e faz só aumento numa vertical? Como é aquela situação?
Yeah, I will talk about that when we talk about sampling methods in a lot more detail, how that's done and how those are related to one another. Is that okay? Okay.
Aí a outra pergunta, vocês medem descarga do leito em algumas estações, essa é a pergunta, e com qual frequência? Porque eu vi que você mostrou alguns métodos alternativos para determinar a descarga do leito, mas vocês devem verificar isso com medições também em campo. Eu queria que você falasse um pouco mais sobre isso, em quantas estações você medem descarga do leito, e naquelas estações onde vocês têm métodos alternativos para determinar a descarga do leito, com que frequência vocês verificam se a relação está bem ajustada ou não?
Yeah, I didn't really present the numbers of stations where we do bed load measurements. I would guess it's much less than the stations where we do suspended. I would say, gosh, Tim, would you say maybe 25% of the stations we probably measure bed load? About 25% of the stations where we do suspended, we measure bed load. It's not commonplace for us, but we do measure bed load, but it's usually not as critical or important for us as suspended. In terms of the surrogate methods, we're much farther behind in the surrogate methods for bed load than we are with suspended. So we're only testing, I'd say it's still very much research phase for that. Compared to suspended. Most of the places where we've tested the surrogate technologies for bed load have been in the Northwest in California, where we've done a lot of hydrophone work, and that's mainly gravel-bedded streams where you can clearly hear the gravel particles hitting one another. And so we'll measure that sound, and then we'll relate it to physical bed load samples that we collect. And then the other place that we've probably tested it most often is in, sand bed rivers like the Missouri, the Mississippi, where we actually do bathymetric surveys and we try to determine how the sand dunes move and quantify how they move and relate that to the amount of sediment that's moving. So.
Vou aproveitar o assunto. Só por curiosidade também, nessas estações onde vocês ou medem, quer dizer, na maioria vocês medem descarga sólida de suspensão, em algumas você medem descarga do leito, ou vocês têm métodos alternativos para descarga do leito, descarga de suspensão, qual é o percentual da descarga do leito relacionada à descarga total? Só por curiosidade em alguma estação, se você tem isso de cabeça, né? Porque assim, normalmente eu tenho um discurso. Primeiro, não é porque a gente não faz aqui, né? Isso tem vários artigos, né, que na maioria dos rios e na maioria das estações, a descarga do leito é um percentual menor da descarga total. Pode ser 5, 10, 15, 20, 30%. Mas só por curiosidade, se você tem esse número relacionado a alguma estação que vocês operam.
Yeah, I would say that at the range of sites where we're measuring bed load or total load, bed load ranges from anywhere from, 7% to 30% of the total load, and it's usually closer to 10 to 20%. So definitely lower than, you know, certainly the lowest percentage of the total concentration. In terms of approaches, I would say most of the sites where we're doing both bed load and suspended, we're doing physical samples and not employing two different kinds of surrogate technologies, or we're using surrogate technologies to help with the suspended, but doing physical samples with the bed load. But yeah, we're still early in our bed load surrogate work, so it's definitely not fully operational, those approaches for bed load. So we still very much rely on physical samples, a bed load pressure difference sample that Tim will talk about to collect sediment samples from the bed, or bed load samples.
Então, desde que a gente começou a ter esse contato com o SGS, para mim, que inclusive eu estou na questão do planejamento operacional, a gente tem um problema aqui no Brasil que nós somos a equipe, a empresa, né, que faz o operacional, ao mesmo tempo a empresa que estaria pesquisando. E a minha pergunta é em relação a esses estudos de inovação ou de aprimoramento das técnicas. Eu queria saber como é a dinâmica de vocês e como que vem a demanda para os temas, né? Se é o público-alvo que consome esses dados e aí se percebe que é interessante pesquisar sobre a fonte, né, dos sedimentos, né? Ou se é alguma coisa que vem das equipes de trabalho, e também se vocês têm assim estações de pesquisa, né? Se você tem alguma estação em que a gente está pensando em analisar tal método ou uma tecnologia nova, e aí vocês têm uma equipe, ou isso é disseminado em todo o país e aí envia esses testes, né, para ser feito pelas equipes de operação, ou se tem um local para testar isso antes e depois tentar aplicar. Como que é esse processo de pesquisa dessas inovações e desses aprimoramentos das técnicas?
So it's a combination of things. So oftentimes people like me and Tim and Mike will have an interest in testing a technology, and we'll do a test using a small amount of money that we may have been given from headquarters, and we just evaluate that at one site. And then if we find that it works, then we talk to other people and they start testing that and evaluating it at their sites. Most of the testing that's been done on some of these techniques have been from USGS scientists in individual offices and states that have been able to, their partner agencies have been interested in testing them at a site where they need very accurate sediment budgets to answer a question. So maybe they know that the 90% of the sediment is being transported during storm events that are very rapid, and they have to have they can't be collecting samples the whole time. And so that partner agency is very interested in paying for the evaluation of these surrogate technologies to give them better, more accurate, and high-resolution data when the sediment is moving to be able to develop a budget. Some other uses of these kinds of technologies have come about from I'm trying to think of some of the possible uses. Development, we have a large regulatory program in the U.S. where we develop limits for sediment loads at a site that are based on time increments that are, say, daily. Like sediment concentrations can't exceed a certain level for a certain amount of consecutive days. And unless you're out there collecting samples every day, you can't answer that question. And so that's been a big reason why our partner agencies have paid for the testing of these technologies, is to give them information at that scale to answer those questions. So yeah, it's a variety of purposes, but we've had a lot of luck having our partner agencies pay us to test these out. And our national programs have had some money to pay for some development of the technologies nationally and the publication of the methods that have been tested. So, yeah. Pedro.
Molly, gostaria de saber sobre a parte de laser, né? Você comentou como tecnologia também aquele SL, né, da Sequoia, que se existe uma pesquisa no sentido de montar algum protocolo do uso dele para medição direta no rio como concentração para obter na integração, né, juntamente com as medições.
Okay. Yeah. So the laser diffraction, the concept is that there's a variety of different instruments. There's the SL that you mentioned, which looks like a sampler, and you lower it in the water, and water comes in through the nozzle. There's also an instrument that I showed that actually has, you mount it in the river, and it stays in that location, and water flows past two lenses. And there's a laser that's shown through the water between those two lenses, and that laser sort of bounces off of all the different sediment particles. And an analyzer on the other side determines, based on all those angles that the laser bounces, it can come up with the size of the sediment. So it can give you size distribution in 32 different size classes, and it gives you what's called a volumetric concentration. So that's the basic of that technology. Testing, we are Tim is currently funding some researchers to test the new SL2 and how well it performs, and he can probably talk about that a little bit more. But in general, what we found is that you still need to, it's a surrogate technology, you still need to relate it to physical samples because it's giving you a volumetric concentration that was kind of developed on an ideal mixture of sediment that may or may not be the same kinds of sediment that you see at your site. So you still do need to do some verification work by collecting samples and relating the response of the instrument to that. I don't know, I hope that there's a day that we can get to when we can use the instrument's data directly, but we're not there yet. Yeah.
Sobre aquela pergunta que eu havia comentado, né, da curva-chave, sedimento, vazão, você podia falar das estações que vocês têm, a maioria tem curva-chave já desenvolvida, ou como é que... Você podia detalhar um pouco isso?
The majority of the stations that I showed on the graph, no, with the daily sites, many of them have a relation between discharge and sediment, well developed. The surrogate sites that I showed another map on, they've already had a rating developed, and we're using those ratings to produce estimates real time of sediment concentration. As far as some of the different approaches for computing those records, Tim will be talking about that on Thursday and some of the different shapes of the ratings and the types of ratings. So that may get at answering your question a little bit better when he talks about that. Yeah. The microphone? Yeah.
Eu queria saber um pouquinho mais sobre os métodos alternativos. Como que lá no SGS vocês testam e depois consideram válido aquilo para a estimativa de concentração de sólidos em suspensão? Qual que é o processo de validação do método?
That's a good question. There is no set standard for how much testing you have to do before it's considered an approved method. We generally like to do some laboratory testing, and then we do field testing in a variety of different environments, different sediment conditions, different hydrology, And once we have that tested in a variety of environments, decide amongst the people who have been testing the procedure, what are the recommended protocols, and then we document that and then produce a report that documents the testing that was done and sort of the recommended procedures. Yeah, there are a lot of things that I presented here that we are not ready to publish a method on because we're still testing them. But like the use of acoustics, that one we feel very comfortable with, and we've produced a method on, a report on how you do that. But we're still evaluating it and still trying to improve the method. So it's not, there's not a set procedure for every technique, but once we've tested it in a variety of environments and we have a group of users that feel comfortable with it and have had good luck with that, good success, then we will publish it. Okay, let's move on to the next one.
Thanks. I just clipped on that on my.
Is it off now?
It's on. When you want to turn it off, you'll flip that switch that way.
I may just turn it off. Okay, I guess we, can everyone hear me? Guess we should move along. We've got a lot of material to cover. So this presentation is going to talk about, I'm going to talk a little bit about reconning a new site that you may be looking at, some site locations, you know, how to select some sites, access to those sites, and then some stream gauges. So I'm Mike Manning. I'm from Mississippi. I work for the USGS. I've been there going on 33 years. This is the location of our Water Science Center now, Here recently, in the last 4 or 5 years, the USGS has begun to combine states, and so we're larger centers to better utilize the resources and people that we have in adjoining states. And so years ago, each state had its own center, but now we're combining states in various places. My water science center is called now the Lower Mississippi Gulf Water Science Center. And so, as you can tell, we are in the middle of the Lower Mississippi River as it empties into the Gulf. I have been working with sediment and water quality on various levels for most of my career. Installing gauges, collecting computing loads early on in my career. Now I've worked more toward being a project manager, and here recently the large river coordinator for our area because we do so much work with large rivers. So later on I'll be talking to you more about that type of work. So I have a few previous careers that you may find amusing. I don't know, some of you may not. But apparently from some of my friends, I have been the coach for the St. Louis Rams, and I look a lot like Jeff Fisher. As you can tell, I guess maybe I do with sunglasses and some of my serious expressions, but I'm afraid not. Another career I guess I've been associated with was Smokey and the Bandit. I've had several friends and coworkers say at times I tend to look a little bit like Burt Reynolds, maybe in my younger days without the gray hair. But anyway, so let's talk about the science. Let's get into site reconnaissance. So we could talk about this for all day, but I'll try to be brief and go through some of the specifics that I have learned over my career. One thing is, it's probably one of the most important first steps that you take in establishing a new site. To get out and look at these sites, see what you're looking at, some of the different features. It takes a little time to do this, but in the long run, this will pay for itself. So, in doing this, you need to devote some time to drive around the basin, to become familiar with the different features, the tributaries, the landforms, things that are going on as far as the land use goes, the bridge crossings in the area, and so forth. You need to be looking at access to the stream and where you can collect your data, the wading sections, low water areas, and even access to the site during high water. Make notes on all of these things and carry this with you. You may need to have landowner permissions to access some of these areas. I know in the U.S., a lot of times we have to go talk to the local landowners before we go onto their property to make sure they're okay with us doing this type of thing. You need to observe the high water and the flood marks, the seed lines, the mud lines on the piers. It'll give you a good indication of some of the extreme events. You need to note the debris around the bridges, how much, the size of it. This can be a good indicator of the energy of the stream and some of the past events that's going on. I know we have in the south, we have several bridges that have a lot of log jams, tree jams that get jammed into the bridges and things. You need to start a dedicated field notebook, of course. A lot of you may already do this, but start this notebook and make notes of what you see and the things that you are observing. Other things that you need to consider, the study objectives. What type of data does the project want to collect? What are they trying to do? And so you can modify, or you can look at these things and know that if this specific site or this location is going to meet those requirements, and allow you to collect the best data possible. You can look back at historical data for the sites. It may have been a site, historical site, that may have some older data that you can look at that will give you some indication of what's been going on. You need to document the physical, or look at the physical characteristics of the area. Maybe the channel slope, the land use, runoff characteristics, regulating structures that may be upstream or downstream that may affect your data collection. The geology, the non-point sources, and observe maybe some different types of hydrologic conditions during the several weeks that you're doing this. Also, you know, it may be beneficial to look at some of the chemical and biological characteristics of the stream. A lot of times gauges are established and then other things are added on, and so just to make notes of these things. One thing that's very important is I suggest to do like a multimeter field parameter survey of the site with turbidity, DO, pH, conductivity, that type of thing, top and bottom at 2 or 3 points in the verticals, and look at the distribution of those parameters. It'll give you a better idea of the mixing of the stream. Other things to consider, you know, what types of data, like I talked about, will it be suspended sediment? Will it include bed material, or maybe possibly later on water quality? The flow measurements, you need to have access to the stream at all stages, flood stages as well as low flow. Will the stream ever be wadeable? You know, at some sites, it's just not wadeable at any point in time. Will you be collecting continuous or automated or discrete sampling, like Molly had talked about, these automatic samplers that can do the job for you when you're not there? Will it have telemetry of continuous data where you establish the gauge? Will you have a clear view of the sky to be able to transmit your data if you're using some sort of data collection platform? And the location of intakes or sensors if you may be installing some sort of continuous monitoring. If you'll be able to connect that to the bridge, if you may have to run this down the bank, and I'll show some pictures later on of these. So site selection. I have come to find out, and I know several that have installed gauges and have done this type of hydrology and monitoring, that the perfect site is not to be found. But if you look at some of these, if you do the recon before this, you can help yourself with a lot of headaches in the future to try to reduce these uncertainties. You need to look at the tributaries upstream of where you're going to be sampling, if that will affect the data and how. Excessive bank erosion, you know, may introduce some bias to your samples. It will, that may not indicate the full basin characteristics. And so you may want to adjust your sampling location to not show some of this. Constrictions as bridges, dams, dikes, flow deflectors, all can greatly affect the suspended sediment transport. So just consider all things and put in the time and effort to do the reconnaissance. You know, not all streams are mixed well. Some are very nice to be able to go out and collect it. They're fairly uniform top to bottom. They have consistent flow. Others have inputs, maybe point source upstream that tend to hug the banks, as you can tell from this tributary just up from this stream here. It may look at the bridge itself fairly well mixed, but just upstream you've got this input of this tributary. This is the Mississippi River at Vicksburg coming off of the Mississippi River into a tributary. And I believe you recognize this picture from one of the sites here in Brazil. And, you know, by the way, with the drone technology nowadays, if you're able to use one of these, it really helps to be able to do that recon upstream and downstream. You can look at that, record the data, go back and play it back. And so it's very, very helpful. So bridge influences. Bridges of all types. Some of them have piers in the water. Some of them constrict the flow. Most times they do because of the restrictions or the piers, the supports in the water. And so this comes off of one of the reports from Guy. It's an older report. It's where he talks about to be sure to consider these types of situations because they can often constrict so that restrict the flow and width, and they may be located at a section where the channel is naturally constricted. So it can also collect the debris, which can, if you're sampling on the downstream or even upstream, it may be just a site that you may want to reconsider moving the site before you establish it there. Most often, sediment collection projects go out and they try to locate their sampling station at pre-existing gauges because there's a gauge already established and the record is there, it has a historical record. But for the most part, when those gauges are established for surface water only, they don't consider it for sediment. So be careful with this. You know, for future sites, try to consider that possibly it may be a site selected for suspended sediment or water quality. You know, you may or may not have an option. Most of the time you may not. They want the site specifically at this location. And so it's just all things to consider. Backwater areas where smaller tributaries are, the confluence is to a larger river, where the larger river controls the smaller tributary and produces backwater effect. This can be a nightmare in data collection for sediment all over the hydrographic conditions. So sample collection access points. They vary according to site. They can be close to the bridge. I find that usually in most situations, bridges tend to have the deeper pool areas because of the scour it may produce upstream or downstream. And most of you guys are familiar with the geomorphology of streams. You know, we have pool areas, the thalweg meanders back and forth. You have point bars and so forth, and cut banks on various locations in the stream. So let's say if a bridge is here or here, you know, you may want to look upstream, downstream. If there's a trail, there could be a crossover where the stream becomes wadable. From the bridge, it may not appear this way, and it may be a slower velocity because the water is deep. But with a little recon, not hard walking or trail cutting, a better site could be found than just sampling at the bridge consistently. There's a good example that I have on a site that we now have operated over 27 years as a sediment and water quality site for one of our national programs. And initially the site was located, and it's a very sluggish stream. It's in the delta of Mississippi, and so there's very little slope. And so it moves, even when on some of the storms, the water may only have a velocity of 3 to 4 foot per second maximum. And so beginning, the folks that were doing this site, they were sampling from the bridge. It's too deep to wade. We haven't been able to find a location. Ecology was added to that site several years later, and these biologists came in to set a reach, a 500-meter reach, to do their macroinvertebrates and algal and fish studies. And in putting in a boat and traveling upstream and downstream, they found an area that was had an input to a small trib, and it put out a bar, that you will, and just upstream or downstream of that was like a beautiful wading section. So, you know, doing a little work and going upstream and downstream, if you can, during lower conditions, you may find a wading site that's accessible, and it's much easier to get out and collect this type of low flow data when you can wade and carry the bottles. Weighting always produces a much better sample, in my opinion, and I think in most, than it does if you can collecting it from a bridge. So access during all conditions. And so we have bridges, boats, cableways, walkways, wading sections. Here's a site on the Mississippi River that has to always be sampled by larger boats, larger samplers. A larger site, but much lower flow conditions, where it can be sampled by smaller boats. Maybe the only way to access the site is on the bridge, with some type of crane sampler here. Or the, whoops, let's go back. Whoops. Huh? Sorry. Wading always is an option. The U.S. has for many years operated cableways because they're in remote areas, and these cableways are anchored with a structure like this. Various types of equipment stretch the cable across. The hydrographer would get into this and he would move this across. He has certain points, and then he can lower the sampler and back up to the cableway and safely back across. This is hard work here, but it may be the only way to collect the sample during high flow. And of course, the extreme events. The USGS is not beyond putting in the perfect gauge at every site, and so we've had situations where our gauges were flooded, and the hydrographers had to go out just before the gauge flooded and move the equipment to the top of the roof line. Here's a couple of this is our data chief here, Mike Runner, and another technician. They have moved this up on the top of the gauge near the peak. They saved the data collection platform, and our continuous data did not stop. In other situations, you just have to do what you can do. But if you do the initial recon and look at maybe some of the higher flow indications, you can have your gauge built up on a platform and try to alleviate some of that, eliminate some of these challenges. So standard gauges in the past were basically designed in the early 60s, 70s, even in the 40s, where there was some sort of intake to the stream. This is a general USGS gauge where there was a concrete structure. This is generalized with a pump house and so forth, although this has telemetry, a data logger, maybe a flow-through pipe. But there's been a big gauge evolution over time. In the 30s and 40s, establishing a gauge and building a gauge was very labor intensive. They would go out and pour these. It would take weeks, upon maybe 3 to 4 weeks, to pour this structure, build this walkway out, and there would be a platform here. And then there would be intake pipes that came in from the stream. And those intake pipes had a series of pumps that they could manually pump out as the sediment would clog that system. And so eventually, though, with the sediment coming in, it would fill in this gauge and it would have to be dug out manually or pumped out. We no longer use these because it's just not feasible for us. And so then the process was the gauges were built on piers and pipes were put in for stilling wells and floats that used encoders that then transmitted those numbers to a data logger. But in today's day and time, this century, more and more of the gauges have a non-contact sensors, radar sensors that can ping the surface, and so we're getting out of the water. And more compact data collection platforms, batteries, the antennas and solar panels and things. And so there's been an evolution of gauges. Construction of gauges. This is, it all depends on the site. As you can imagine, the smaller sites are fairly easy to do and look at. You may be able to just build a simple platform to elevate your gauge above the high water and place the solar panels. And this gauge here has an automatic pumping sampler here. It has a system to where it can either be, as Molly said, operated by stage or flow or different trigger points. But if you are pumping any sample, automatic samples, there's a limitation to the lift that these pumps can pull the water. And so that has to be taken into consideration. So if you have any intakes that go to gauges, that's probably one of the highest challenges, one of the greatest challenges is where to place the intakes for the data. Whether you're collecting maybe water quality parameters, or in this case, this has a pipe that's going up the side of this concrete wall. Fairly easy to install because at low water, a ladder could be put up here. This can be bolted in, and the conduit run down the edge of this up to the gauge. You can see here, this is more than likely an intake for an automatic pumping sampler. There were tests done that showed actually the placement of that intake, and it did not need to be pointed upstream or downstream, but out to parallel of the flow. Now you've got to have on these pipes for water quality sensors access points, and so different shots here that show how this can be secured to the stream bed and accessible. So you have to be able to access these things at different hydrologic conditions. So here are two pipes that are going down a stream bank that are built on a metal frame. They're supported, they're secured. They have apparently found that this will stay in the water most of the time, even during low flow. It has a clean out door where they can open this and retrieve the cables or the sensor. This is a protective pipe that goes, it's a flexible pipe that they probably buried in the ground to the gauge for communication. But there's always the issue and the challenge of being able to keep the probes in at low water. It varies from site to site. There's not always an ideal location where you can get a gauge on maybe an abandoned bridge pier and go down and maybe attach this. It may be you can get a ladder right here, and there are technicians that can go up, and then technicians that can help from below. And once this is mounted, then you can, get your gauge up and operating. There may be a challenge here with the sunlight on the solar panels, and so I talked a little bit about that, about making sure that you've got access to the sky. Then there are the larger channels, which come larger problems. Some of these bridges, you may be able to fix the gauge on the handrail. You'll have to be able to get out to the bridge. Some of these bridges have walkways. Some of them just have the curbs that run along. And so there's a challenge there with traffic and being able to get out and maintain the gauge. Here's a log jam, but they've got this attached to the downstream of the pier to try to protect the orifices. And I'm not sure if these are different intakes for different stages. The same here, but you can see the mud line and some of the historical flood indicators of where the water level will be at some time or has been in the past. Here's a wire weight gauge for external reference. This is the bridge at Vicksburg, the highway bridge that goes over the Mississippi River. It's almost impossible to get out to do anything here. Although back in the 70s, there were a few hydrographers that were successful in putting a PVC, a plastic pipe, down that pier, and they had a sensor in there. And this upper bridge is closed. This is an older bridge, and the new interstate bridge is on the downstream side. This is actually a historical marker. And so they were able to put that pipe down this pier. I won't tell you exactly how they did it because it was very unsafe. Well, I'll go ahead and tell you. So what they did was they had a technician on the top, and they put a pulley up here. They had a boat with 3 in the boat with a harness. They put the rope through the pulley and back down to the boat, and they had a man sit in that harness, and they backed the boat up, and they raised him up the pier, and he drilled into the pier and put the brackets. The only problem was when these barges come by and leave these wakes, the boat in the back was doing this, and he was up and down the pier. I do not recommend this at all. So there are more sophisticated deployments of gauges where we have a multitude of probes, YSIs, velocity index sensors, where we feel like it needs to be in more of a protective cage because this is very expensive. These cages are located on an I-beam, and so it has a crank where they can crank these heavy cages up and down to service the probes. This is a nitrate sensor. This is a Suna nitrate sensor. And of course, they have to do this because of the fouling of the sensors to maintain those probes. The new age gauges that the USGS has started deploying since the major Hurricane Katrina that we experienced in the Gulf, where we lost a lot of our gauges due to the storm. They have our hydrologic instrumentation facility started designing these gauges, and they're called rapid deployment gauges. And this is one of sorts. I think this is the first version, but it all comes assembled. And so this bracket is fixed to where it can be mounted to most handrails very quickly. And then there's another pipe that comes in. All of this is very lightweight. It's aluminum. 2 hydrographers can go out and install this in about 45 minutes. The gauge is already assembled. It has a solar panel. It's got a battery. It's got a radar sensor. It's pre-wired. And all of this can be installed in 45 minutes to less than an hour and have this data recording. There are cables that securely lock this to the bridge so that vandals can't come and try to remove it. Now, these aren't really meant for permanent installations, but for, you know, maybe collecting data, you're experiencing maybe some sort of storm or hurricane, and you need to get out and collect to see what's going on at that site. These are very handy. So, cost for gauges. This is a broad subject. I can give you some basic information here, but it all depends on how far and how complex the gauges can and will be, of course. Most of the sondes that collect water quality parameters start at around $16,000 or 64,000 reals and can rise up rapidly depending if you're going to a Suna nitrate sensor and so forth. The typical USGS gauge, surface water gauge with a stage sensor, telemetry capabilities, including labor, somewhere around the installation of about $17,000 at 68,000 reals. That's basic. Maybe a little cheaper if a radar sensor is not used, if some sort of pressure sensor can be there, and if it's a smaller site. What we call the O&M, the operation and maintenance of a gauge of this sort, to go out and routine measure it for flow measurements, and including the data computations, around $15,000 or $62,000 a year operation. We have a series of offshore gauges in the Gulf of Mexico, off of the coast of Mississippi, Louisiana, and Alabama, that we monitor salinity and some other parameters, turbidity, for some of the restoration work that's going on in that area that's funded by the Corps of Engineers. This was one of the original gauges that we tried to use, but after one of the hurricane events, it destroyed those gauges, and we were able to get funding and go back and harden these gauges with steel. These are very expensive gauges. There aren't many of them that we operate with the USGS, but there are a few, and I just wanted to relay that to you. The new generation of sensors that are coming out are allowing us to get out of the water, non-contact, and so really get off the bridges and so forth. As you well know, the Dopplers and some of the tether boats that we're using allows us not to have so much equipment on the boat, a laptop, a tether boat, and within about 30 minutes make a complete discharge measurement. Of course, drones, you all are very much aware of those. But these video and still cameras that our surface water networks are researching and looking into, I don't have particular information about them, but they're taking pictures of the control sections of the river. And so they can look at the movement of sand and point bars as they're coming down the stream. This helps them work the data and adjust the ratings and the shifts that they have to put on their information. And also the video still cameras, or some of the actual live cams. This is a particular research that we did on the Mississippi River at Vicksburg back in 2016. We had a collaboration of about 6 different water science centers. During the flood on the Mississippi River, it happened in the winter, in January. It was an unusual flood. And so we had several of our top researchers come down, and it was set up in working with some of our other offices in Denver, where we did a non-contact streamflow measurement on the Mississippi River. We had a U.S. Border Patrol drone fly that site at about 35,000 feet. They videoed the site as we had ground-based boats making Doppler measurements. We had video cameras video the surface velocity. And what they do is they take the surface velocity, and there is a normal relationship to where the highest velocity is at the top, and then it tapers down to closer or lower velocities toward the bottom of the channel. And they were able to use this thermal infrared video co-collected with the ground-based data, and the actual data that we measured with ADCPs at the site was a little, was about 1,699,000 CFS, or 47 cubic meters. The difference was about 4%. And when the guy called me and he said, "Mike, I've got a little preliminary data to show you," and I said, "What? You can measure this from a drone within 4%? He said, "We're working toward that." And so this is, I think, where we're going in the future. Don't know how far, how long it will take. I tried to get these folks to come back and maybe do this work again and continue this. But what they're wanting to do is get this out in the remote areas where it's just unable to get there, and they can do this by drone or even satellite imagery. Questions? Yes.
Eu tenho uma relação à seção de medição, né, da coleta de sedimentos. Para a medição de vazão, a gente geralmente escolhe o melhor local, né, em função das características hidráulicas no momento da visita. Para a coleta de sedimentos, isso é uma prática adequada, uma vez que eu mudando o trecho, eu posso estar mudando também o aporte de sedimentos por algum problema de margem ou algo do tipo?
I would say it would be the best to try to keep it in the same location. If there are no inputs or influences from other tributaries, if you feel like the discharge or the flow measurement would be accurately or the same as it would be maybe upstream, if there is a say a walkway that's within visual distance, it's site dependent. But yes, you need to keep it within the same flow regime. You would not want to move the sediment site where there's other inputs and tributaries that could add inputs, and so that you're relative with your discharge. Does that answer your question pretty much? Yeah, right.
Obrigado. Eu ia fazer exatamente essa mesma pergunta do Ricardo. Assim, hoje em dia, a gente poderia fazer até diferente, mas como aqui no Brasil, lá nos Estados Unidos, eles usavam, né, como a Molly mostrou, o metro igual ao incremento de largura, no metro igual ao incremento de largura, obrigatoriamente você tem que ter profundidades e velocidades. Não é? Então, estaria amarrado no passado, por essa condição, fazer no mesmo local. Ou então medir, pelo menos, profundidade e velocidade onde você escolheria para fazer a amostragem de sedimento, porque você precisaria, para utilizar o metro igual de largura, a profundidade e a velocidade. Hoje, com medidores acústicos, aí talvez, mas como o Mike falou, que eles não fazem, né? Teria essa discussão, mas no passado estaria amarrado fazer, porque você precisa de profundidades e velocidades para fazer a amostragem de sedimento de suspensão pelo metro igual ao incremento de largura.
That's correct. That's correct.
Deixa eu aproveitar que o microfone está comigo. Só uma pergunta, Mike. Sobre 2 pontos. Poços tranquilizantes, que você mencionou aí que tem um alto custo, hoje em dia, parece no SGS, não estão utilizando mais, tem aquela questão de entupimento daquela tubulação que conecta com o rio. E outro é sobre a utilização lá dos teleféricos, do cables. Como é que está isso hoje no SGS, né? Especificamente relacionado aos teleféricos, que aqui no Brasil nós não temos praticamente nenhum. O CPRM, eu acho que não tem nenhum, no passado até já teve. E até é bom a gente não ter, porque eles são muito perigosos, né? Com a questão da... Ainda tem alguém deve ter aí. É muito perigoso. Então, eu queria saber como é que está hoje no SGS a questão da utilização de teleféricos e poços tranquilizantes, né? Pelo que eu entendi da apresentação, parece que estão migrando já para estruturas já de pontes, que é mais fácil, mais barato, do que construir um poço tranquilizante e a própria utilização do teleférico.
Yes, the cableways. We've never operated one in my center, but Arkansas has 1 or 2, I believe, that they still use because it's in such a remote area, in a valley that the bridge is maybe too dangerous, and in the past had the funding to install something like this. And so, yes, they are dangerous. It's not something that we routinely install nowadays. There were some type of cable apparatuses where the actual hydrographer didn't get in the carriage, and it was a motorized where they could motorize the reel out to the river and operate. Even now, I think there are a few where they operate the tether boat down, and they can slowly operate that and move it across the stream and so forth. You know, Tennessee had a lot of these cableways back in the coal hydrology years, where they were, that was the only way they could collect their data. One of my early project chiefs and mentors would tell me these stories about being on this cableway, and you see this tree coming down the river, and it would catch your cable, and he said all you could do was hold on, you know. And so, yes, they are very dangerous, and we're not installing those more and more now. We're trying to get out of the river, non-contact type sensors, like the radar for stage and so forth. But still, we have a good many that we still are in the river. The concrete structures, the old Gages back from the 40s, there's a hazard of methane gas because of the sediments that sit in there. And so our safety program started this very rigorous having to test the air and blow air in for someone that had to go down and pump that sediment out. And so the influx of water could come back into that stilling well. We've decommissioned almost all of those in the United States. You know, we're at the point now where we can move on and do better than that technology. But back then, that was the only way that they could figure out how to do this. So,
Mike?
Yes.
Can I say something about cableways? We have a lot of cableways where I am in the western U.S. because they're with low population and a lot of public land. There are not many roads and bridges and things like that, so a lot of remote sites, and so cableways are often the only way to get across the river. So we have a lot, but the USGS has a program that some people are certified to be cableway inspectors. Mm-hmm. So they'll travel around and they'll inspect cableways on a certain interval to make sure that they're safe. And every cableway has some specifications for, what's the maximum flow, water level that you can safely operate that gauge for different purposes, that cableway for different purposes, knowing that you've got sampling equipment and the sag and the line and that kind of thing. So they are still heavily used, particularly out west, but they're inspected regularly. I mean, there are certain flows that it's scary to be out on those, and but often that's probably the least scary way to get across the river instead of actually being physically on the water surface.
Mike, você comentou da escolha dos locais das sessões, né? Porém, assim, planejamento da rede, vamos dizer, vocês costumam fazer mais voltado para um objetivo específicos ou para bacias? Poderia falar um pouco mais disso? Como é que é essa metodologia da escolha dos locais em grande escala, vamos dizer, né?
Large scale as in how large of a basin? Like 10,000 square or larger sites for larger? It takes a lot of work. So you have to know the specifics of your cooperator, the actual design of the project and what they're wanting to look at. If it's just higher flows, there are other means to collect data from bridges. But as far as selecting the site, they may limit you to a certain location. There may not be other types of, you may not have that much leniency to move the site. So it all depends on the direction and of your program, your project. If you have a little leniency, you may be able to move upstream a couple of miles to a better location, a less traveled bridge with lower traffic. But there are certain situations where you may be limited with that.
Por exemplo, no Mississippi, o principal foco ali seria para navegação. O objetivo da rede de sedimento no Mississippi.
Right. So as far as like the Mississippi River, that's not the main objective for our work there on the river. Most of the work there is water quality related. Sediment is attached to that. We do have other programs where we are collecting specific sediment data for the Corps of Engineers and the work that they do. They're very interested in looking at the energy of the stream, the sand transport, the bed load, and that sort of thing. And so we even explained to them at higher flows, we have to move to a different location in the channel because of the way that the water is out in the floodplain. And so we document that for each of those samples. We may have to move downstream 4 or 5 miles in order to collect the data where the water's all encapsulated within one area so that we're not missing because of the overbank flow. You know, I know the Amazon has a lot of overbank flow in high flow season. So that's even more challenging to address that. But there are different situations on the Mississippi River. Some of them are very complex where we collect the data in one location, but we may use an upstream gauge for the computation of discharge. And it's difficult because that planning was not done at the same time. And that has been the historical gauge, like at St. Francisville. And then years later, there was a water quality station that was established at St. Francisville, but the discharge actually is computed several miles upstream at Tarbert Landing, because at St. Francisville, it's a poor site for the gauging because of overbank there. And so different situations like that. Does that answer your question? It may be at the discharge has to be computed at a couple of different tribs and combined for that location. We have site just at Vicksburg on the Yazoo River where we have a lot of flood control structures. And so the gauging is done at 2 flood control structures and combined for the downstream water quality collection. So does that answer your question? Right. Yes, sir.
Eu tenho uma impressão muito semelhante quando a gente teve o treinamento de qualidade de água, em que o foco de pesquisa e de trabalho de vocês é assim para olhar para esse rio, né, para esse curso d'água e olhar todos os parâmetros que são mais acessíveis ou visíveis e estudar a relação entre eles, para que eu possa monitorar isso de uma maneira mais efetiva e não dependa tanto da coleta física. E é o que eu percebo, assim, a impressão que me dá é que a coleta física de vocês, a coleta, né, real, não é o monitoramento em si, mas é um dado que vai vir dar um embasamento para eu estabelecer essas relações entre os parâmetros e poder monitorar esse rio de uma maneira mais efetiva, mesmo em lugares em que eu tenha dificuldade de fazer a coleta. Eu só queria saber se a minha impressão está correta ou não, porque para mim está mudando muito os conceitos com esses treinamentos nesse sentido, porque a gente confunde muito a coleta com o monitoramento, né? E o que eu vejo é que a coleta ela é uma balizadora do monitoramento que realmente que eu quero. Eu não sei se é isso, eu queria entender se a impressão que eu tenho está correta.
I think what you're trying to ask is, and I think I understand where you're coming from, and it's kind of like the example I had on the non-contact flow measurements. We had ground-based data to calibrate that data, and so Molly and Tim do a lot of work with the surrogate type data, and so that we can use the ground base and actually the stream collected samples to calibrate that model. And so there's always going to be some degree of that, you know, to check the models or to check the curves. Like Molly had talked about the box coefficients. Box coefficients are, the terminology there comes from an observer where we had a sampler mounted in a box, and he could go out and lower that sampler down every day and take a 1-point sample in the middle of the stream, collect that. He lived locally. And so we would install this for him, and then he would collect those, and we could use those with our continuous data to see if we needed to shift our continuous data or our curves, our sediment curves, to model it. Sometimes some shifts, sometimes not that much at all. They're really very, correlated very well. Does that answer your question for the most part? I think that's, but yes, the ground-based data is always going to be there for now, I think, for our immediate time frames until we can really quantify these models and these curves or these surrogates, because we've got so much going on in these new surrogates in satellite and colorimetry pictures from NASA, looking at the different colors of streams and things, being able to look at harmful algal blooms, the HABs and things like that, coliform. So, yes,
Porque aqui no Brasil a gente tem uma dificuldade muito grande de acesso, e eu fico pensando se não seria melhor a gente trabalhar dessa forma em a estação em que eu tiver a possibilidade de fazer esse monitoramento completo, todos os dados que eu conseguir fazer, de eu explorar essa estação ao máximo para conseguir descobrir essas relações e calibrar o modelo, como você falou, e poder aplicá-lo em estações mais remotas em que eu tenho uma dificuldade de fazer a coleta efetiva, né? Então, eu acho que, porque a gente, pelo menos eu, estava trabalhando muito com essa visão de tentar melhorar o método de coleta para que eu possa conseguir coletar em todos os pontos. E na verdade, talvez não seja o ideal. O ideal seja tentar achar soluções intermediárias entre as situações que a gente encontra. E quando eu achar a situação ideal, eu explorar ela ao máximo possível para poder embasar o trabalho em outras situações. Então, acho que é mais ou menos o mesmo direcionamento.
And it could be a little different from site to site. Your correlations, of course, with all models and so forth.
Então, Manning, muito obrigado pela presença de você aqui, primeiramente. É um prazer poder trocar essa experiência, pelo menos para mim, que está sendo a primeira vez em contato com vocês, do SGS. Está sendo muito enriquecedor. Eu tive uma dúvida a respeito das estratégias de técnica na apresentação da Molly. A respeito da técnica para estimar o sedimento, que ela mostrou 3 gráficos na apresentação anterior. Se eu não me engano, teve um por difusão a laser, o outro por transdutor de pressão em caso de altas cargas, e teve um outro, deixa eu lembrar, o medidor acústico, sedimento. O primeiro gráfico que ela mostrou, a curva não acompanhava tão bem o previsto, vamos dizer assim. Eu acabei perdendo qual era a técnica aplicada naquilo ali, porque é muito diferente da forma que a gente aqui no Brasil estima ou quantifica esse sedimento, lá como a gente tem com a ajuda da Magda, do laboratório. Eu queria saber o seguinte, se nesse primeiro gráfico essa técnica tradicional, e quando comparada às 2 outras demais técnicas que vocês usam, que é a medição acústica ou difusão a laser, qual era a técnica daquele gráfico anterior, que eu não consegui captar, eu não consegui entender. Para os dois. Mas ele deve saber.
Ela não está aqui, não.
Yeah, Molly left for a meeting. I think she had to, but I can try to answer that the best way, and then she can follow up. I can try to answer that the best I can until Molly returns. She had a short meeting to run off to, but I believe I know the slide you're talking about. Is it the one where it showed just the individual cross-sectional points, and then she plotted the turbidity, and or was it maybe the laser diffraction? I think that process goes over a multitude of hydrologic conditions for particular sites, and I would defer more to her to see exactly how they're addressing that. But back to calibrating, and so a lot of this research is ongoing, to see if these sensors and these turbidity sensors, they're coming out with different ones now, are working over the entire range. And so you may see at some point that they correlate very well with the samples that we're actually taking on the bridge, but then during different situations, they may be lower or higher. And so there's probably always going to be that checkpoints to make sure that those shifts, and so those shifts can be varied over time or in different situations. So does that kind of maybe answer that? Tim, I don't know, can you add to that?
Yeah, I just wanted to add that later in the week she's going to talk a little bit more about those, the surrogates and things. So you'll get another opportunity to see some of those plots, and she'll talk about it in more detail. Today was kind of just a quick overview of things.
More to come.
O que eu lembro do slide era exatamente ela falando isso. Se você pegar só as coletas espaçadas, o máximo que tinha sido coletado, né, registrado, era 250, não lembro qual era a unidade. E quando usou métodos alternativos em que fez essa calibração a partir das coletas físicas, então se identificou, acho que quase 600, né, o pico, aí podendo ser feito isso por várias técnicas, que a primeira acho que foi turbidez, e aí depois ela apresentou, acho que a análise de laser e outra coisa. Mas era...
Vamos deixar para a Molly vai explicar quando ela tiver.
Não, mas eu só estou trazendo... O foco era que só as coletas espaçadas não vai dar para a gente uma visão...
Só para a gente conseguir passar todas as apresentações. Alguém tem mais alguma pergunta? Só para a gente não... Vou ter que controlar um pouquinho o tempo. É lógico que todo mundo pode participar, perguntar. É só para a gente conseguir passar por todas as apresentações, né?
Na verdade, só reforçar um pouco o que você disse, inclusive, para a resposta do Roberto, em relação ao que o Roberto falou. Os métodos alternativos hoje têm sido trabalhados muito por estação. A calibração por site de monitoramento, né? A gente não tem ainda um monitoramento em uma estação para tentar extrapolar para uma outra, né? Porque você pode ter modificação de uso, ocupação, tipo de solo, geomorfologia. Então, só deixar claro que hoje a linha de trabalho tem sido por estação. Então, mesmo uma estação remota, ia ter que ter uma campanha de coletas para calibrar para aquela estação específica.
Bom ponto, Ricardo. Regionalização de vazões já é uma complicação, ainda mais de sedimento, né? Ok, alguém tem mais alguma pergunta? Se não, vamos fazer o seguinte, eu acho que ninguém está cansado ainda. Teoricamente, teria um intervalo aqui. Não sei se o time prefere o intervalo agora ou já prefere fazer a apresentação. Que a próxima apresentação é a sua, né?
Let's take a break now.
Ok.
Break, and then
Então,
we've got 2 more before lunch that will...
Tá bom. Então, vamos fazer o seguinte, só para a gente conseguir concluir a agenda de hoje, tudo certinho, são 10h03, 10h18 a gente volta, em ponto. Obrigado, Mike. Thank you. Ok, pessoal, vamos retomar para a gente conseguir cumprir a agenda. Bora, pessoal. Vamos? Fechou? Ok.
All right, thank you for the opportunity to be here. I'm very excited. On now?
That's okay.
All right, thank you for the opportunity to be here. I'm very excited to be here. Some great questions already. I see that you struggle with some of the same things that we struggle with, so I'm looking forward to the discussion as we continue on this week. As I mentioned yesterday, I worked for the USGS for about 25 years. I started as a student in college, and I just stayed working for the USGS. It's a nice place to work. For the last couple of years, I've been the chief of the Federal Interagency Sedimentation Project, and I work for that project about half-time. And then about half-time, I supervise a nutrient and sediment team for Illinois, Missouri, and Iowa. So if you saw the map that Mike presented, it's just the states right north of there. My office is about 2.5 hours south of Chicago. So that's where I flew out of to come here. So anyway, yeah, today, this presentation, I'm going to talk about the types and functions of suspended sediment samplers. Wazan did a great job yesterday, which makes my job easier today. But I'll launch right in. So before I talk about the samplers, I think this group in particular all knows very well why we want to focus so much on the samplers, and because we want a representative sample. And this is a neat image of, this is what you normally see from an ADCP, right? The velocity or the backscatter data. And Molly's going to talk a little bit later this week about some research, and it's really in kind of a research stage of how we're using that backscatter data to convert it to, in this case, it's suspended sediment concentration on the y-axis here, and on the y-axis over here it's depth. And then the colors goes from 40 milligrams per liter to 140 milligrams per liter. And so you can see across this cross-section, if you just go and just grab a sample from the bank, you're not going to get a very representative sample of what is going on in the full cross-section. So hopefully maybe in the future this is something we can use to determine where to take our samples, even better than EWI or EDI. But that's where we're at now, is the EWIs and EDIs. This is really more research, but it shows why we need good samplers to take representative cross-sections in the full depths. And so, as you know, there's a lot of different sources of uncertainty or bias in our way we sample, and the samplers are one of them, and that's what I'm going to mainly talk about in this presentation, but we'll talk about some of these other ones in the other presentations. So early in the sampling in the U.S., there were multiple agencies using multiple different samplers. You can see some of them here. A lot of them were more of an open bottle where they lower it with the bottle closed and then some mechanism to open it up. And as Wazan talked yesterday, you can think about some of the problems that this might have caused, the non-isokinetic and things. There's a few more samplers. Again, more open bottle. Maybe starting to look a little bit more like what we use today here. These are all in FISP reports on our website. And then these are more for the measuring the bed load, which I'll talk about in my afternoon presentation. So in about 1939, all the agencies were getting together thinking that, we compare data across agencies and throughout the U.S., we need to come up with more standard samplers. And that's when the FISP was created. And you can see here, we've got the, on your presentations that you have available, we've got the this is the current FISP web address. And you can go there and get a multitude of things. Oops, wrong button. One of the main things you can go get, what Walzan showed, is all the work and reports that have been done on samplers. And then a lot of my current work is focused on these surrogate instruments. And we have a page on the website called Research. And if you look there, it outlines some of the research we've done in recent years and are continue to do, and hopefully partner with more and more people like you and others from other countries as we try to advance our technologies. But the samplers are going to be around for a long time because we need ways to calibrate those, because they're all usually site-specific calibrations and things, so you need samples and things to calibrate to the different new instruments. And so for the samplers, I mentioned I work about half-time for FISP. There's another person at our hydrologic instrumentation facility. He works about 30% to half-time on more of the physical samplers, maintaining them, testing them, and that's where we sell them. And so my talk is going to be a little bit like Walzan yesterday. So to keep it interesting, I'm going to have a quiz a little later. And I got a prize from our HIF. It's a keychain that floats in the water. Just to keep it a little interesting, so I'll have a quiz. So you see how good you listened to Walzan yesterday. But I like this because it's the HIF. So to note that there's two parts of kind of FISP. That there's my role overseeing a lot of the surrogates and some of the sampler stuff, the tests, but that the HIF really does the testing and maintenance of those samplers these days. It used to be in the old days a lot bigger staff and everything, so it's kind of funding has dwindled and things, but we still get by and we do a lot of interesting things. So types of samplers. There's the mode of sediment transport, the mode of sampler deployment, the ability to collect representative isokinetic samplers, the ability to collect uncontaminated water quality samplers. That became a big thing for the USGS in about the 1980s, and the mode of operation. So I'm going to lay out the samplers in kind of some of these different categories, and then we'll talk about them in more detail. So here's the types of samplers. So we have suspended sediment. So that's the sediment that's pretty much in most of the water column. And then we have the bed load. And I'll talk about the bed load more in the presentation later this afternoon. But that's the particles that are kind of rolling or saltating along the bottom. And then we have bed material. So that's just the sediment that's on the bottom. And you want to go and collect a sediment sample for that. Those samples drive a lot of the sediment models and things, and I'll talk more about that later. So this presentation is focused mostly on suspended sediment. All right, so here's where we have a little quiz. We've got this sampler here is the DH81. So for the coveted prize of a HIF floating keychain, can anybody tell me what the D, the H, and the 81 stand for? You want to use the microphone just so everybody else can?
Depth, handling, and the year of it was developed.
Correct. Here you go. So it's the depth integrating handheld. So you can see I can hold this with my hand and lower it down. and it was developed in 1981. And so this one is as you can see, it's got a plastic bottle to it, and it really comes in 3 parts. This is what similar to a DH48, what you would use, but the water quality folks like it because it doesn't have any metal. So if you're doing trace metals with water quality, that's the problem with the other. So it's got a nozzle, and it comes apart. Like that. So this is, keep this with it, and so I'll pass this around. And I'll keep this up here just so nobody's hitting each other in the head or anything. All right, so, and then we have some bigger samplers that can also be used more from a bridge that are handheld. So they're lighter. And then this is a bed material sample I'll talk a little about later. And then the suspension deployed. So the heavier samplers can go through the faster velocities, a point sampler here and a bag sampler here, and another newer point sampler here. So then the types of samplers. So the suspended sediment over here, so you can see the metal casings, and then, like I mentioned, in the 1980s, they started developing some water quality ones. These ones here with the white epoxy, again, to get away from the trace metals. Point integrating versus depth integrating with the bottles and with the bags. And just to talk about the components, I think most of you are familiar with this, but just the stabilizer fin, the sample container, the body, the air exhaust, which is very important to make sure that is open so that the air is escaping the bottle as it's filling, and the intake nozzle. This is a zoom in of the nozzle, and it's important to note we've had some problem with manufacturers and getting this width exactly right, and Mike's going to talk about it a little bit in a minute. Note there's also supposed to be a taper on the tail to overcome some of the friction that happens in the nozzle, so that you can make sure that these nozzles are isokinetic. So the key sample characteristics, the maximum velocity of what they can be used. You don't want to use it for outside of these ranges. The sample volume, sampler weight, deployment, unsampled zone, and again, depth integrating versus point, and then isokinetic and non-isokinetic. So in the fifth series of samplers, we have the US denotes United States, D for depth integrating, which we got that one under control, it sounds like, and then P for point sampler. The H is the handheld or hand line, and then the year, and then bed load or bed material. And Walzan talked about this report. It's a really nice report, and I'll be using some of the same images today. Lays out the different samplers, and it's available on the web. So when we go to suspended sediment sampling, you go either depth integrating or point integrating, and then you can choose if you're going to weightable, so you come down to the DH48 or the DH81, depths greater than up to 15 feet. And sorry, I have to apologize for the U.S. for not switching to metric. When I was a kid in school, grade school, there was this big push. The U.S. was going to switch to metric, and I didn't realize how big a deal that would be. now in my career that when they, I don't know, for whatever reason, the U.S. didn't switch to metric, and so now we're still stuck in Englishness. But anyway, and I don't have these converted, but walls on slides are really nice because you've converted most of this to. All right, so then depths to 37 feet, and then 110 feet, and 220 feet. And these samplers here are very similar, and Mike's going to talk quite a bit more about these later, but just the heavier sampler to get down with the velocities and the depths. And then for water quality, same type of flow chart, decisions on your different depths. As you can see, there's some of the same samplers on this one, especially with the newer ones that can do water quality. And again, just the charts that were shown yesterday. This is kind of a complete chart, all the way from the depth integrated hand lines through as you get to bigger depths and higher velocities, the bigger samplers, you start to get into the bag samplers, and then the point samples also. So when we talk about samplers, ideally we want the isokinetic, but sometimes this is just a weighted bottle sampler. So you put a bottle in it and lower it down, and it fills up. It's pretty much getting your surface sample because it fills up really quick. This is the type of sampler Molly was talking about earlier, called the pump sampler, where there's an actual line down to the river that has an intake, and then there's a pump in here that pumps the water up, and then it puts the water into one of these bottles, and the arm in that thing rotates, and once it fills one sample, it'll go to the next sample. So isokinetic. Walzon really hit this hard yesterday, but I'll just read this. To obtain a sample in such a way that the water sediment mixture moves with no significant change in velocity as it leaves the ambient flow and enters the sampler intake. It's a critical step toward collecting a representative sample. And so here you see what we want, the isokinetic. The velocity of ambient water is the same as the velocity that goes into the sampler. We don't want this, where the velocity in the nozzle is less, because then you're going to have a sampler with higher concentration. And then the opposite is where the velocity goes higher in the nozzle, and you have a less concentration going into your bottle. And Mike, did you want to talk about those nozzles that you brought? And I can. Now, I think it would be, yeah.
So I can usually talk loud enough without a microphone because my voice carries.
They might. I think they need it for the.
Oh, they need it.
Yes.
So I don't want to take up a lot of time of Tim's time because we are running a little bit behind, but I wanted to share this with you. And so what I brought is a variety of these newer nozzles, if you want to call them that. They're Teflon. They're for various samplers, even the one that the DH81 that Tim showed here. But these are examples of nozzles that I have taken out of the sequence of using. In our clean room where we clean items every week and we're cleaning and things, and what has happened is over time the nozzles are in the samplers, and as the hydrographer is bringing the sampler up, it may accidentally hit the bridge, or they drop it, or different things happen to it. So you can look at these. I'll pass these around. The one that I really liked showing is, if you can tell, this one's bent. It's actually cracked. This would probably have an efficiency of about 10%. I don't know. And it's also clogged with dirt. It was jammed in the mud, which can be cleaned out, but if this were to happen in the stream bed, and so there are others that you can see and they're just deformed. And so I wanted to take these and pass them around and you can look at them. These type of Teflon nozzles are not recyclable. So once they're damaged, they have to be discarded. The process in which the heat and everything in the polymer process they go through to develop these Teflon, why? Because they're non-stick for water quality purposes. I don't think I have a plastic one, but you've got some plastic nozzles that you brought that are strictly for just water quality. But we'll pass these around and let you guys look at these. So if these nozzles become deformed in any way, this is out the window, as you can tell. So just be aware of your nozzles and inspect them, look at them, look at all of them, and if you find some that have been damaged, just set them aside and discard them is the best thing.
All right, so this plot here, is something I want to spend a little time on because I think this will answer some of the questions from yesterday. What we have on the y-axis is the air in concentration, and on the x-axis is the intake efficiency. So that's the mean intake velocity over the mean stream velocity. So we want to be right at 1. So there's 0 air in concentration. And then on this side, there's a positive bias and a negative bias. So what does that mean? On the positive bias, that means we're in this situation right here, where we're getting more concentration in the sample than we want. And then the negative bias is we're getting less concentration than what we want. So the neat thing about this, and there's an old FISP report on this, and this is an updated modern version that was in a different publication, but what it shows here is, so if we have less efficiency, so we think we're getting more sample in our bottle than what we want, it's a pretty big deal for sands. Not so much for the silts and clays. So just some statistics here. The bias in suspended sediment concentration for coarse sand is about plus 10% for intake efficiency of 0.75 at 5 feet per second. So we're backing off here. So about so we got 1, 0.9, 0.8, 0.7, so we're right in here, and we're going over about 10% air. And then bias in suspended sediment concentration for less than 0.062 millimeters, which is the fines, the silts, and the clays, is less than 10% for an intake efficiency of 0.2 at 5 feet per second. So that's way over here, and we're still less than 10%. And then just to drive it home a little bit further, say we have equal parts of each size of sediment. So each size of these sediments, we got 25% of each one of these. Based on, this is the bias. So at 0.8, we have 3.5% bias, 0.75, 4.9. And then at 0.5, we have 13.1. So that's if you have a mix of sand and silts of all these combined. And then kind of a separate statistic, but just in sampling in general, in these publications here, based on replicate samples at concentrations above 20 milligrams per liter, suspended sediment difference of plus or minus 10% are common. So it's just saying in your, you go across the river more than one time taking samples, you're going to have, there's some air just in the sampling itself. So then you kind of put that on the backdrop of the bias that you get for the intake efficiencies. And then you make decisions as an agency of what is acceptable. So non-ice kinetic conditions, if sand has been shown to be negligible in prior analysis of the samples collected at sites that under similar conditions. So take the example your bag sampler or our bag samplers in low velocities, they don't do very well for intake efficiency. But at those low velocities, how much sand is actually moving is the question. And so if in those velocities, if you can show that it's mostly silts and clays, so if your intake efficiency is a little bit lower, you know, maybe you're not inducing as much air as what you might have originally thought. Was that useful? Are there any questions on that? I know it's a kind of a complicated plot and things. Maybe stop for questions at this point.
Tim, tem algum relatório do SGS publicado que mostra essa pesquisa que foi feita? Que, por sinal, é interessantíssimo isso aí, porque mostra exatamente o impacto, a pessoa entende mais fácil por que a eficiência é importante, não é? Se isso tem algum relatório do SGS publicado, disponível.
Yes, I'll send you the links to the report. There's an old FISP report, and then there's this actual image is from something that Mark Landers and John Gray put together. It's more of a summary of sediment sampling that I'll put. I should have had the link on here, but I'll send you the links to that. All right, so moving on, again, depth integrating, you got the bottle samples, various different types. This is an important point Wazan pointed out yesterday, is that as the water's flowing in, that air is exhausting, so that gives you a limit on how much water that you want to fill. So for a 1 liter bottle, as you were saying yesterday, it's 800 milliliters. And this is the transit rate. I'm going to go through this one. It's kind of a modern depiction of it, but I kind of like the old ones better because they depict. So we have two problems with the bottle samplers: the approach angle limit and then the compression depth limit. For the sake of time, I won't go into that. Wazan covered that really well yesterday. If there's any questions, we can talk more about that. Again, looking at and then for the different nozzle sizes and things, you may not be able to get all the way to the 15 feet, the compression depth limit. So then just going through some of the different samplers and looking at the characteristics, the D95, is just an example of one of the ones that with the bottle samplers that has that 15-foot depth problem. So then we move to the bag samplers for deeper depths, and you get away from the compression problems because it's a bag that starts with ideally with no air in it is what we're shooting for. And the bag fills up, and you can take it to deeper depths. As you can see here, with the DH2 for the different nozzles, you can go up to 35 feet. It's a fairly light sample, as well as I was talking about yesterday. So then we have the bigger ones, the D96, and then the D99. And Mike's going to talk quite a bit about large river sampling, where we use these samplers. So I'm going to go just past these for the sake of time. And then, but I do want to stay a little bit on these. So this is the intake efficiencies that were done for developing the D96. So as you can see on the x-axis, we have ambient velocity from 0 to 9 feet per second, and inflow efficiency on the y-axis. And so as you can see, at these higher velocities, we're doing okay, but then it really starts to drop off as you get to the lower velocities, and even we don't recommend using it below the 1.5 or 2 feet per second. But as we know, as Michael talked a little bit more later on the logistics of when you're below those conditions. But as you can see, for these conditions here, we're between 0.9 and 1.15. And if you take into account the graph that I spent some time on to show you the accuracy of the concentrations at those ranges, we felt comfortable with releasing the sampler in about 1996. We do know not only the bag samplers in low velocity, but there's a problem with bag samplers in colder temperatures. As you can see here, as the temperatures get colder, the intake efficiency drops. So here, again, on the y-axis, we have intake efficiency, and now on the x-axis, we have water temperature. So that's something to consider. And I mean, in my mind, it kind of makes sense if you think about a bag or even a balloon. If it's frozen or or really cold, it's much harder to blow up than if it's in a hotter temperature. And plus, just the properties of the water when the temperatures are colder. And then so now again we have intake efficiency on the y-axis, and now we have sample volume on the x-axis. So as the sample volume gets larger, the intake efficiency gets lower. And that would probably be for pretty much any bottle, even the bottle samplers and things. But with the bag, this shows what happens with the bag. But you're still within a 0.9 to 1.1 range. So what do we do to know what this intake efficiency is in the field? And it sounds like with your program and things that you do this for every vertical and things, is that you get an intake efficiency test. So you know the ambient flow velocity, you know the sample duration, the nozzle size, so you know what the sample volume should be, and then you compare that to what you actually get, and that's how you get your intake efficiency. And we have a policy saying that we want people to do this each time they take a sample. And maybe we'll end up backing off that a little bit as we get more information on the bag samplers and things that are more testing. There was some concern, like with the colder temperatures and the lower velocities and things. But beyond that, we were getting some strange lower intake efficiencies for higher velocities that we weren't really expecting. But we think, and Mike will talk a little bit more about this later, is it ended up being the nozzles that we're getting from the manufacturer, and the tolerances that we have on those criteria, and some of the manual adjustments to the nozzles that FISP historically did, but we weren't doing as of maybe 10 or so years ago. And then so anyway, yeah, Mike's in the thick of all that, and he'll talk about that a little bit with his presentation on the large river sampling. So point samplers, I just want to talk briefly about this because I know that you don't use them. We don't use them as much either, but they're used for some of our research and even some of the sites that Mike's involved with, the Corps of Engineers. They want the point samplers, and for the modeling, they want to know what the sediment concentration, how it varies in the vertical, and then the particle sizes at the bottom versus at the top and things. So point samplers are good for that. It uses this diving bell principle, which I actually have a little experiment here I'll do and show, because that's a little bit confusing to people. But just to show the schematic of the sampler first, this is the top view of the sampler, and this is a side view of the sampler. So as the water, and then there's this compression chamber in the sampler. That's disconnected from the where the bottle goes. So the water comes in and or comes up and it compresses this air in the compression chamber. So why would we want to do that? So we say we lower this point sampler and it's closed, and we lower it to 30 feet. So you got this hydrostatic pressure at the nozzle that is really high, but we have to have some way to compensate that in the bottle, or otherwise when we open up the nozzle, the pressure doesn't, the water is just going to gush in. So what happens with this, and I've got a schematic that shows this a little bit better, is so this is the compression chamber, and there, when we lower it down, the nozzle is closed, the exhaust is closed. So no water is getting into the sample container, although we have this compression chamber which is open to the bottom. And then so the water can come up a little bit in there and compress the air to what is at the nozzle, and because it's connected through this tube to the sample container. So then what we do is open the nozzle by a trigger in the boat and a solenoid in the sampler, and open the exhaust so air can come out. And then, but at that time the compression tube closes, so then you can get an isokinetic sample. And to show that, so you might say, well, if you have that open to the bottom, so this in the bottom of the sampler is open, you might say, why doesn't the water just come up, and when you have it in this state, why doesn't the water come up and get into your sample container? So just keep things a little interesting. Assume this is our compression chamber, and this is our sample container up in there, just for it. So that's completely dry, and let me put a little more water in here. And maybe I'll go to the center of the room here so more people can see. So this is the diving bell principle. There's videos on this on the internet and things, but I thought I'd show you today. So I'm going to lower this just like we lower our sampler. So the compression chamber and then the sample bottle in there. And bring it back up. So there's a little bit of water on the lip, but when I pull out it's actually toilet paper from the hotel. It's not a sampling container, but it's dry. So that's the diving bell principle. It's pretty neat how those point samplers use that to make it so that they're isokinetic when they get lowered down to a certain depth. What's that? I thought they're... No. So the piece, we have a few different samplers. We have this point samplers. We have the P61. So 1961 technology. And as you can see here, there are lots of parts. Lots of things that can go wrong with the sampler also. It works really well, but it's a little harder to maintain. There is a newer version of it called the P6, so 2006. And as you can see, quite a few less parts and easier to maintain, obviously. But this is the solenoid that actually actuates that nozzle to open and the exhaust to open also. There's a diagram of it. And then there's also a heavier version for deeper depths. And again, this is just a summary of all the different samplers. And with that, I'll take any questions.
Ô, Tim, só 3 perguntas. Vocês ainda estão utilizando o amostrador DH48 ou a maioria das equipes já substituíram, preferem utilizar o DH 81, principalmente porque ele é mais leve.
There's teams that still use the DH48. Yeah, it's a perfectly good sampler for sediment, and if people have that in their office, that's what they would use rather than buy the DH81. Yeah, and the weight of it is not a big deal between the two. It's more if they need to do something with water quality, they would maybe, and even so I say water quality, you know, it's mainly like the trace metals and things that might cause a problem with the metal samplers, where if you're doing nutrients, you know, maybe DH48 is just fine.
Achei interessante também de quando é aquele memorando que vocês recomendam ou exigem o teste de eficiência nos amostradores com container flexível em campo para as equipes. Não sei se você lembra qual o ano daquele memorando.
Yeah, I can get you that information. That was a few years ago when Mark Landers was the FISP chief. I think he came in 2015 here. Yeah. Do you remember what year, Molly? I mean, it's on our website. I can.
2013.
Yeah.
Mas a principal razão para isso foi algum amostrador específico, tipo o DH2, qualquer outro lá com container flexível, ou foi em geral porque vocês estavam notando que a eficiência dos amostradores com container flexível não estavam bons em campo, apesar de ter sido aprovado nos testes? Porque, isso, na minha opinião pessoal, os amostradores com containers rígidos, eles são ótimos, não é? Então, o que nós usamos aqui, o DH48, o DH59 e o D49, eles funcionam muito bem, porque o container é rígido, a água entra e o ar sai. Quando a gente tem a restrição da profundidade, aí a gente tem que usar o pontual ou flexível. Só que o flexível realmente tem que ter muito cuidado quando dobra aquela saca. Essa saca o saco está rígido, o container flexível está rígido ou não. Então, a gente tem notado aqui no Brasil também que isso varia muito em campo. Então, o mesmo amostrador, quando você desce e sobe, tem hora que ele vem com 1 litro, tem hora que ele vem com 400 ml. Então, tem que ter muito cuidado na utilização. Não sei se vocês perceberam isso na utilização de campo. É lógico que o DH2, que a gente usa aqui também no Brasil, ele dá bem menos problema, inclusive em campo, né? Queria saber só se você lembra qual foi a motivação principal da publicação desse memorando.
Yeah, the main reason was just some of the work that people were seeing and doing intake efficiencies. And so it wasn't mandatory before the memo. So, but there were some research groups that were really looking at it and doing intake efficiencies, and starting to have some questions. And they were mainly looking at in cold water environments. And so it made Mark, the FISP chief at the time, you know, rethink and want to take do some more testing. And part of that is, well, people are using them all the time at these bigger depths and things. So he said, when you're using it, just go ahead and do an intake efficiency, so that we have a database to start to look at it in more detail. And Mike actually did some testing on the large rivers with very detailed sampling, and where we were just talking about it in the car ride here, to maybe do some more of that and look and make sure that the nozzles at that time with the new testing are not a question. We need to take that factor out, because that's, Mark went into some, and you'll see on our research page on the FISPA, there's some research on the nozzles and some three-dimensional modeling of the nozzles and things. So yeah, it's been a real question with the bag sampler. Well, was it the nozzle, the bag, or just some combination and things? So we're definitely still looking at that. And but yeah, I think a big part was that there's just some mixed information with nozzles in manufacturing.
Minha última pergunta, você mostrou aí o amostrador pontual P6. Vocês estão utilizando ou ele está em pesquisa ainda? Ou vocês já estão utilizando de forma operacional na rede de vocês?
We're using the P6. So when it came out with the actual 2006 number on it, that's when it became active for use. So there's still people that have the P61 and use that. Perfectly good sampler, but as people are doing more sampling and things, especially the folks on the lower Mississippi, that they've got the P6, the P6 200, and things to do their sampling there.
A minha pergunta também está relacionada ao memorando de entendimento que o Alson lembrou agora. Esse teste de eficiência realizado antes da medição, antes da coleta, ele tem a mesma faixa de limitação entre 10%, similar ao teste que o FISP faz, ou é algo mais permissível, uma vez que você está no campo, é muito mais difícil você controlar a velocidade, etc.
Mike, is the tolerance 20%, right?
On the efficiencies in the field?
Yeah, the efficiencies
it's
7.
And 70 above. But normally for like, well, for example, we send the sampler down. So I believe, and Molly, you may correct, I believe earlier, and this may change, but the minimum efficiency for any sample, and I don't think most field crews stick to this because they feel like they can do better. There's something happened during the sample, but 70% or better was considered okay. But normally, we're way above that with our efficiencies. And so, for one instance, we'll send the sampler down, collect the sample, we'll weigh it, we have the velocity, we can calculate what volume we should have received, we'll calculate the efficiency. If we come up with 92, we keep that same transit rate. We'll keep that sample as a sediment sample, and then maybe send the sampler back down with the same rates and use that as a water quality sample. Molly, is that something different?
Yeah, so I'm looking at the memo, and I had to refresh my own memory on that. But the procedure is to do the test 3 times, and if the average intake efficiency is plus or minus 25%, and each individual test is within plus or minus 30%, then you can proceed with collecting the sample.
Yeah. So but for the most part, I don't think our field crews we can do much better and feel much better than 70. But with the 10%, with other factors that may influence that, there may be certain situations that may be the best that's possible, especially in moving boat situations where the boat is actually moving around and you're not at a fixed point. And so, yeah.
So maybe to give Molly enough time to get done before lunch, want to switch over?
I just may want to add a couple of things while Molly's getting ready to talk. When these new samplers and this Teflon equipment and these new style samplers were being developed, our national program at the time was involved in a lot of trace metal parts per billion sampling. And so there was a large need to have a sampler that was non-contaminating for those type samples. And so this was a several $100 million project that Congress funded for the USGS to go out, assess the status and trends of the nation's water. In doing that and that much money being spent, there were new protocols, the parts per billion protocols that we have in our national field manual that was developed. And so these Teflon and these epoxy-coated samplers became a big push in that era. This was back in the early 90s. And so from sediment samplers, yes, the ones that have always been used, the D48, the 74, those are still used today, but the new Teflon plastic type bottle samplers are multi-purpose samplers.
Okay. Okay. Can you hear me? Okay. Okay. So in this presentation, we're going to focus on suspended sediment sampling techniques. So we've talked a lot about this. Walson talked a lot about techniques, and some of the same techniques that you follow are the ones we follow. So I think in this presentation, I will focus more on what are the slight differences, and then what are some of the other techniques that we use for suspended sediment sampling that maybe that you don't use or that you haven't considered or that we use for specific purposes. So we'll go into more detail on those. So for those of you who know Art Horowitz in USGS, this was a graphic he used to like to present to a lot of people, is that most of us know when we're doing some kind of a computer model or a computer program or something like that, if we're putting garbage data, bad data into it, we're going to get bad data out of it. And the same thing for when we send our samples to the lab. If we do a bad job of collecting the sample, we're going to get garbage information, trash information back from the lab. It's not going to be good quality data. So we have to start at the beginning when we're collecting our samples and make sure that we are doing everything that we can to ensure that we are collecting a good quality representative sample. So to do that, we need to be considerate of how sediment varies in a channel. And most of us have an awareness of this. But sometimes if we go to a new site, we may not know how sediment varies at a new site that we've never had any experience with. So it's important to stop and think about the river, think about what kinds of sediment may be moving and how it's moving at that site when you're considering what approaches might be most appropriate for that site. So sediment concentration typically will vary by depth, particularly the sand concentration. And the sand concentration will typically increase as you go lower in the water column. The size of the sediment will typically be larger as you get lower in the water column, where it takes more energy to suspend those larger particles. So there is variation with depth. There's also commonly variations across a river. Maybe you have a confluence, another river coming in upstream that's contributing different levels of sediment, and there's not complete mixing of the sediment by the time it gets to the site where you want to measure it. So you need to have an awareness of how that varies across the river. And that distribution or that variation can also change over time. This is a site that's influenced by tides, and this is a graphic showing the sediment concentration in this color scale. So the darker colors are the higher sediment concentrations. And so this is during one portion of the tidal cycle, the ebb tide, and this is what's considered the flood tide. So the water is coming in, and then the water is going out, and as it's doing that, it's carrying sediment differently. And so there is variation over time as to where in the channel sediment is being transported. And we can see that at sites that aren't tidally influenced, different flow conditions where sediment may be transported in one portion of the river during one hydrologic condition, but then that changes in another hydrologic condition. So having an awareness of how that happens is useful for determining the best approaches for measuring sediment. In USGS, these are our typical size categories for sediment, and I'm guessing that this is similar for you all, but clay-sized particles are less than about 4 microns. Silt-sized particles are between 4 and 62 microns, and that split between sand and silt is an important one for us. And sand-sized particles go from that point up to about 2 millimeters, and then really we're in gravel-sized particles above that level. So these are our general categories of sediment that we analyze for. And a lot of times we will analyze for a much more detailed gradation within each of these categories, particularly the sand-sized particles. So considering all of that we talked about, all the site-specific considerations, we want to consider those things when we're deciding how to collect a representative sample. And Wallison covered this really well, that we have to get a sample. We can't possibly measure all of the water that's moving in the river. We can't possibly get it. If we could, that would tell us how much sediment was moving, but we can't. So we're trying to get a sample that represents what is going on in the full cross-section. So we're trying to use techniques that allow us to get the most representative sample possible that's representative of the full stream cross-section. So I'll cover some of our sampling techniques. So some of the most common ones that we use are, depth integrated. We've talked about those. Tim and Wallison talked about those. Tim also talked about point sampling and point integrated sampling, and we'll talk about that again briefly. We also sometimes have to sample non-isokinetically by collecting grab samples or non-isokinetic verticals. Sometimes I mentioned we use pumped samplers to collect samples from a single point in the river. So those are all considered non-isokinetic methods. So we'll talk about when each of those is appropriate for us to use. We've covered the whole concept of isokinetic sampling really well. We just want to make sure that the velocity of the water coming into the nozzle is the same as the velocity around the nozzle in the river to ensure that the concentrations coming into the nozzle are the same that are flowing around the sampler. So to do that, we need to consider several things: the sampler that's used, the nozzle that's used, the raising and lowering rates, and other practices. So you want to make sure that those are appropriate, and you also want to make sure that you don't overfill your sample container, your bag or your flexible container, your flexible container, bag, or rigid container. So Tim talked about this too. Again, as water is coming into your sampling container, the air that's in this container is being exhausted out of that port. And so I'm sure Tim mentioned this, is you need to make sure that that port is not clogged so that air can escape as it's being raised and lowered. So that's one step. So depth integrating, we're going to multiple locations across the channel. We're lowering it through the water column to ensure representation of the entire water column, pulling it back up, and then we'll move to the next section. So the most common techniques that we implement with the depth integrated techniques are the EWI, the EDI, and then there are times when we collect a depth integrated sample only in a single vertical, and we'll talk about that. So equal width increments. So this is the procedure that we follow. We will divide the cross section into 10 to 20 sections of equal width. The first section is actually half of the width of each section. So let's say we have a 100-meter river, and we divide that up into 10 sections. Each section is 10 meters. So our first station will be at 5 meters. And then the next station will be at 10 meters beyond that, so 15 meters, 25 meters, 35, so on and on and on. So the first section is just the most confusing, is that it's the half of the width of the section. So we would define the vertical transit rate, the raising and lowering rate that's appropriate, by going to the deepest and fastest flowing section, and that we talked about that a lot yesterday. That's typically where we will define what's appropriate, and we want to try to maximize somewhat the sample that we get and pick the transit rate based on that. Once we pick that transit rate, we'll use that same rate at all of the sections. And then there are, of course, considerations for the transit rate for each sampler and nozzle size, but for them, we all want to make sure that we are less than about 4/10 times the average velocity in that vertical. You get above that, your transit rate is too fast. You'll collect a sample at the center of each of those sections. Make sure you don't overfill any sample bottle. And then we were talking about this yesterday with Walson. A lot of times what we will do in USGS is we'll go to, say, the sections on the edges, and we'll raise and lower the sampler down. And when it comes back up along the edges where we have lower velocities and lower depths, we'll only get a very small amount of sample. So often what we will do is we'll go to the very next section and add to that same sample, and we'll get a little bit more. And then maybe go to the next one, raise it and lower it and raise it, and we'll add a little bit more. The problem with that is if you go to too many sections and you overfill the bottle, what do you have to do? You have to go all the way back to the beginning, and start over. So that's a gamble. So you've got to be careful not to do that. But that's commonly what we'll do. And in the deeper sections, we'll usually just, each section is its own sample. And we'll either cap the bottle and submit it as part of the sample set, or in some cases, we'll composite it into a larger container on site. With this method, we've talked about this, that each sample bottle, because you're using the same transit rate, but you've got different velocities and depths at each location, each sample bottle, the sample you collect at each section will have different volumes. And with the EWI, the common practice is to composite all of those. And we generally suggest that people collect replicate passes, so in what we call an A and a B pass, so 2 sets of EWI samples. It's not official policy, it's not an official requirement, but it's a recommendation to better understand the variability in a sample over the conditions over which you're sampling and the sampling practices. So that's a general recommendation. So graphically, this is what the equal width increment might look like, except that the graphic is really truncated not to show the full number of sections. So you get a small volume of water on the edge, and then as you go out to the deeper, faster sections, your volume is going to increase. And then these number of sections, number of verticals will increase until you get to the maximum number that you've selected for the river. 10 to 20 is typical. So here's a picture for those of you who know Mark Landers with USGS. That's Mark looking very serious and mean. He's usually not serious and mean like that. But here he is at each station. He's collecting a sample, and then he's putting the sample bottles next to each station and along the bridge. So he can look at volumes, he can compare sample, the sediment content in each bottle, and ensure that he's collected a sample from each location. And then when he's done, looking at all those compared across the section, you'll see that this was a site that probably was a pretty deep and fast vertical. And over here, it looks like maybe there was maybe a slight island or something like that. It was shallower depth, lower velocities, maybe close to a bridge pier or something here. And then it got deeper faster again. You get more sample volume. And then, yeah, so he was just able to compare all the sample volumes and sediment content across all the stations. So the other technique that we're using more and more commonly, you have a question?
Nas orientações que você deu do igual incremento de largura, você colocou que a velocidade de trânsito tem que ser menor do que 0,4 da velocidade média na vertical mais rápida, né? Tá.
Correct.
Porque pode ser que essa velocidade seja maior em outras verticais. Então, a questão é só na vertical mais rápida.
Well, I mean, ideally you would be determining that where you've got the fastest velocities. There could be some variation if you've got a section that may be a little shallower, but you have higher velocities. You might want to consider setting your transit rate at that section because you're concerned about exceeding that limit. You might want to consider that one even though it's not the deepest section.
A minha preocupação são nas outras verticais em que a velocidade vai ser menor. Então, se essa velocidade de trânsito, dependendo da vertical que for menor, se isso tem alguma influência na questão da isocinética, né? Da eficiência, isso.
Trying to think how to answer that. Let's see. When you're setting your transit rate at the deepest, fastest, you're setting it so that you maximize your volume collected at that location. But still, and to do that, you'll be kind of erring on the side of the low side of the acceptable limits of transit rates. So when you go to apply that same transit rate to other sections, you should still be okay because you're kind of erring on the lower side of the range that's possible for that section. Okay, equal discharge increment. Do this. So this one, generally the same procedure that you seem to follow is that you would need to determine the discharge, so you would need to either make a flow measurement prior to the sample collection or determine the discharge from the rating that's developed at the site, if there's a strong rating. And then you want to divide your cross-section up into, in the range of 4 to 9 sections. 5 is very typical for us. Sections of equal discharge. So every 20% of discharge is what we're dividing that section into. You're going to collect a sample at the center of each of those sections. Whoa, I hit something bad. Okay, so again, you don't want to overfill your sample bottle. That's important. But your transit rate will vary at each section based on the average velocity there and the depths. So at each section, that will vary. You're going to be adjusting that transit rate to be appropriate for that. And ideally, as Walson mentioned, ideally, if you do it right, you should get the same sample volume at each vertical. That's the goal. You don't have to with this method, but that ideally will give you the best quality sample. And then, again, you have to be sure that your transit rate is less than 0.4 times the average velocity in each individual vertical. And then what you can do is, if you've got all the same sample volume, you can composite those samples, or you can always analyze each bottle individually. And we'll talk a little more about the value of analyzing EDI bottles individually. Again, with EWI, we generally recommend people collect 2 passes, so 2 sample sets across the section, and compare the change or the variability in the 2, but it's not required. So graphically, again, this is what an EDI sample would look like, where we've got, certainly the spacing is different. It's targeted at sections of equal discharge. And if we do it correctly with the correct transit rates for each section, we get roughly the same volume of sediment. So these are the reasons that we typically think of when we're evaluating whether to use EDI versus EWI. The value of EWI is it's very simple calculation. Anybody could go out to the site and calculate where they need to collect a sample. You don't have to know what the discharge is to implement it. You don't have to make that measurement. And it can be a better choice when you have a lot of variation in concentration across the section. When the river is poorly mixed, or some of the pictures that I showed that you could clearly see horizontal variation in concentration on the surface, and you can imagine that that is occurring throughout the water column, then EWI might be more appropriate because you're measuring more sections and you can pick up that variation across the river a little better than you can with EDI. The value of EDI is that it technically should take less time to collect the sample because there are fewer verticals that you're sampling, 5 typically versus 10 to 20. And if you analyze each bottle separately, it can be much easier to see problems in your sampling. It can be easier to see if your nozzle hit a sand dune or your sampler hit the bed really hard and stirred up a lot of bed sediment. It can be easier to see that if you analyze each bottle individually. And that's possible with EDI. So another approach that we sometimes take is called single vertical sampling. And this could be implemented if, let's say, we have, at some of our stations, we have what's called an observer. So this is a member of the public or someone from a partner agency that's closer to the site than we are that will collect sediment data for us. Is that something you ever have at ANA and CPRM? Is that something, observers, people who collect data for you that are like citizens or anything like that? Yeah, okay. So this is something that we use sometimes. So to avoid them having to collect a full sample and do the computations associated with that, sometimes we'll have them collect a sample from a single vertical or a single point. Another reason we might use this is if we're, let's say, conditions are changing extremely rapidly at the site and we want to get a snapshot of the sediment conditions at that one point in time. And if we were to collect a full cross-section sample, things would be changing so rapidly during that storm event that we wouldn't be representing a snapshot, a single condition in time. So we might get a single vertical and use that information. But we never consider that sample representative of the cross-section until we take it an additional step. So first, let me talk about how we collect that sample, and then I'll talk about how we relate it to the cross-section. So to determine where we collect that single vertical, ideally we would do it based on a location of equal discharge. And the best place to take it would be the point in the cross-section where the average SSC, or average concentration, occurs over the largest range in stage, which is hard to determine. But basically, you want to pick a location where you would expect sediment concentrations to vary proportionally with the overall cross-section over a range in conditions. That's going to give you a good relationship for comparing the two types of samples. So when you're collecting the samples, we use the slowest transit rate possible without overfilling the sample bottle. So just like when we collect the representative vertical for EWI, we want to err on the side of the slowest transit rate that's going to give us the maximum sample volume without overfilling. And then what we do is we take the value of that sample and we will periodically collect also a full cross-section EWI or EDI and compare those two numbers. We'll do that over a range of conditions, and then ultimately we will develop a relationship between what the single vertical is telling us and what the full cross-section concentration should be. So we'll talk more about this later. So I want to go back briefly to transit rates for depth integrated samplers. We've talked a lot about this, but I want to just touch graphically on a few more things. This is an example if you were lowering the sampler too slow in the water column, what will happen is this sample, whoops, oh, I do this. This is bad. Sorry. Okay, what will happen is you get water in here, that bottle fills up, and then as more water comes in, the sediment drops out and you get clean water going out of that exhaust port or the vent. So what you were essentially doing is losing clean water and concentrating the sediment in your sample. So when you overfill, you get too high of a concentration in your resulting sample. When you go too fast, the pressure is not able to equalize within the sample bottle relative to the outside. So you're getting insufficient sample coming in, and it's not representative of what's moving around the sampler. So ideally, all of those things would be in happy agreement with one another. You're not overfilling the bottle, but you're allowing the sampler enough time to equalize the pressure there as you're going, and you get a representative sample. So we have a series of tables that we rely on too. In addition to the graphs that Tim presented that show you the operational range, we also have these set of tables that we can follow that you can, each sampler and nozzle combination has its own table. And we take these with us sometimes, and it's a table of the depth of the water. And I apologize, our tables are in feet, of course. And then the stream velocity in the vertical is along the top. So for, say, 10 feet of depth, for example, with a D96 sampler, which has a 3-liter bag and a 1/4 of an inch nozzle, we can, let's say we've got 6 feet per second velocities. Our transit rate can be anywhere between 0.4 and 2.4 feet per second to be able to operate that sampler isokinetically. So it's just a nice thing that we can take with us in the field. All this kind of thing is embedded in Alvaro's Hydrosedimentos program. So you all have it way better than we do, I think. But the same kind of concept is this is telling you, giving your conditions, this is the operating transit rate that you can use at that vertical. Okay, so we'll talk about point samplers, and Tim talked about the use of the P6 and the P61, the P63, those options, and he mentioned that some people like to use these kinds of samplers particularly to get information about how sand concentrations are varying throughout the channel, particularly for modeling purposes. We also use it, we've got a method that we're testing now for using down-looking acoustic Doppler current profilers that you would use for flow measurements, using those to estimate suspended sediment concentration. And to develop the relation there, the current protocol requires the collection of point samples. And we follow kind of a scheme like this, where we collect point samples at each of these locations, and we match those results up to the acoustic Doppler data that's collected closest to that location. So a couple of different cases where we use the point sampler. And there are two approaches really. You can lower it to each location, open that nozzle, and allow it to collect for a short period of time and then retrieve that sample. Or you can velocity weight it and collect a full fill time, a full bag, or a full sample volume given the velocity at that location. So you can do it on a set time interval at each location, or the time interval may change depending on the velocity at that point. So two different approaches. And you can, depending on the objectives of your study, you can analyze each sample individually, or you can composite it at all the locations where you're sampling to get a picture of the cross-sectional average. So there's another picture we've seen before. That's the P6 200, the heavier P6. There's another picture deployed off of a bridge with a crane. So there are cases where we've mentioned that we have to collect samples that are not isokinetic. Either the velocity is too low, and typically that's when we have to do this. And so the flow conditions, usually the velocity, or other circumstances require using our general depth integrated isokinetic samplers unusable. And so, yeah, generally this is when we're below the operating limit of each sampler, low velocities, and typically in those conditions, sediment is usually well mixed. Most of the types of sediment in transport are fine, real fine sediments that are generally considered well mixed anyway. The samples that we collect are not considered fully representative or integrated, but given that our depth integrated isokinetic samplers don't collect isokinetically at low velocities, this is the best that we can do. And the typical, these are a couple of types of equipment that we can use for those samplers, for those samples. This is a weighted bottle sampler, and it's just like a vessel or container that you put your sampling bottle in, and you lower it into the water using a rope or something like that. This is some kind of, it looks like a PVC pipe that's threaded into this cap, and so water is coming into the top of the bottle through the mouth here as you raise and lower it from the pipe. So yeah, this is another example of that weighted bottle sampler. This is a, looks like a pint bottle or a glass bottle with a cap on it that's got a little hole in the top. So they're collecting a depth integrated sample as it's being lowered and raised, but water is restricted a little bit because there's just a small hole in that cap to prevent it from overfilling before you can bring it back up. So we talked about auto samplers or pump samplers. We use these very frequently in the USGS to collect samples when we can't be there, particularly at sites that have storm events that cause very rapid changes in flow and sediment transport. And it's nice to have these that are automatically activated to collect samples throughout that event, so we don't have to be on site. And then we can go later to retrieve the bottles, process them, ship them to the lab, and get information throughout the event. We can activate or trigger them to sample based on a set time interval, or water level, or flow, or if we've got a turbidity probe or something like that, we can trigger it or activate it based on that data. So we treat pump samples the same as, say, like a single vertical or a grab sample, in that in themselves, they don't tell us everything about what's passing the site. What we have to do is relate the concentration at that intake location to the overall cross-section sample. So by doing that, we develop what's called a box coefficient. And I'll talk about that. Okay, this is a picture of a typical pump sampler. Yeah, it's got the motor assembly here up top, and it's got a panel that you can configure or program the instrument. And it's got a rotating arm that goes around, and there's a tubing that goes up through that arm and out into the river where there's an intake. And so the pump pumps water from into the intake, up the tubing, down into this arm, and that arm turns and inserts the sample into a number of bottles. You can get this with different kinds of sample bottles. This is set up with 24 1-liter containers. You can get one big bottle container that it dumps everything into. There's different types of bottles. So the concept of box coefficients. So we consider these to be correction factors to convert the sample you would get at a single point or a single vertical to what the overall cross-section should be. And we calculate them by the cross-section concentration divided by the point concentration. So a typical approach for us would be, over a range of conditions, we would go to the site at the times that we would collect our full cross-section EWI or EDI, and then at the same time we would force a sample from the pump sampler, or we would collect a single vertical, analyze those two types of samples, and then we would look at the concentrations and compare them to calculate the box coefficient. And we would do that over a range of sediment and hydrologic conditions. Once we understand how that relationship varies over a range of conditions, we can calculate the box coefficients and then apply those corrections to every sample that we collected using the pump sampler or that single vertical. If that number, that ratio, that coefficient is always 1, that means that the location where you're collecting your single vertical or your pumped sample is completely representative of the average concentration in the cross-section, okay? Usually it will vary a little bit. So just to show you what that looks like graphically, this is a river cross-section with only fine sediment passing through it. And these lines indicate concentration contours of those fines concentrations. So it varies between 900 to 950 milligrams per liter. Not a tremendous amount of variation in fines concentration throughout the section. And that's typical for fines. And this means that you could collect a single vertical or a grab sample or put the intake for your auto sampler at any location within the channel, and you would get something that was pretty close to the overall average concentration. So if you collected it here, for example, the box coefficient would be 1.1. If you collected your intake for your pump sample here, the box coefficient is 1.03. So very close to 1 overall. So you would be pretty safe collecting from anywhere within the section for fines. Now sand, as you can imagine, is different, and this is showing you how that sand concentrations vary from 700 to 3,000 as you go across the channel and as you go down in the channel to the deepest parts. Here you need to be a little bit more considerate of where you collect that grab sample or that single vertical or place the intake for your pump sample. Because the box coefficient can change dramatically depending on where that's done. So here, the box coefficient would be 5. So you would have to multiply every grab sample times 5 to get to a corrected cross-section value. But here, the auto sampler intake, if you collected here, you'd be close to 1.7, which is not bad, fairly close to 1. So, yeah, you just need to be aware of that when types of sediment moving and where it's moving to properly determine where you should collect grab or single verticals, and then also where you might put the intake for a pumped sampler. So this is an example of a site, the same site that I showed previously, where they were collecting the EWI sample. So they collected their EWI sample, and then at the same time, they forced the pump sampler to collect a separate sample so they could relate that value to the cross-section. So after we've collected those pairs of samples over a range, there are a number of ways we can look at how the box coefficient varies. The first step is typically just to plot what the concentration was in that grab sample or single vertical or pumped sample versus the full cross-section EWI or EDI, and see if there is a linear relationship between those two. If we don't see a linear relationship over a range of conditions, we can go some additional steps and look at how that ratio or coefficient varies over time, over seasons, or also over flow. Because sometimes the sediment distribution may change in your channel over different seasonal conditions. Maybe you have vegetation growing in certain parts of your channel that changes the distribution, or the sediment sources are different in different seasons, which causes a change in the response. Or at different flows, maybe that relationship or the distribution of sediment changes. So these are additional things that we can look at. Once we have an idea of how that coefficient varies, if it's constant over the range of conditions, or if it changes over different seasons or flows, we can then apply that correction factor to all of our point or grab or pump sample data to get what it should have been if it were a full cross-section sample. So that is a typical thing that we will do to maximize the types of samples we're able to get, but also represent those, have those be representative of the cross-section. Okay. Computing EDI stations using ADCPs. Now, Alvaro, I'm always excited to see your program because I think it's amazing. And I think there are so many things that we can do in the USGS to adopt what you've done and use it, because I think the tools that we have are in different pieces of software, and pulling them all together as you have would be a major benefit to us. So I look forward to testing your program more. I'm glad that it's in English now, that we can start trying it out at our stations. But I'll tell you what we do typically to compute our stations, particularly for EDIs. So remember, with EDI, you've got to know the flow distribution. And most of the time, we're determining flow distribution based on an ADCP measurement, a moving boat ADCP measurement. So Dave Mueller, who many of you know in the USGS, developed the EDI program. And it used to be a standalone piece of software that you could use, but now it is embedded in his QRev program for processing ADCP measurements. How many people know what QRev is or have? Almost everybody. Good, good. Okay, good. So now it's a little box in the corner. After you've processed your discharge measurement in EDI, you can click on that box and have it compute your EDI stations. So this is a free program. It was developed by Dave Mueller. And it was compiled originally with MATLAB, but now as Dave is changing to Python format, it will be in a compiled Python program. And it's compatible with RDI and Sontec ADCPs, but moving boat measurements only. So unfortunately, like that's one thing, your ability to do the flow tracker and current meter measurements and things like that is not something we have built in. So it would be great to have that ability as you have in Hydrosedimentos. Okay, so the goal with us when we do it is we always want to try to maintain a straight line path when we're making our ADCP measurements. And then so when we pull the measurement in and process it in QRev, then this is the button that we can click on, this EDI. It allows you to select the transect that you want to use. So this could be the one that you felt like was the straightest transect possible. It doesn't matter if that transect starts on the left or the right bank. Once you pick the one that you want to use, you click OK. And then a window will open. There is a box at the top that says 0 distance offset. And if you hadn't started your discharge measurement at, if 0 wasn't the edge of water where you started your discharge measurement, you could put in an offset here. So one example of if you were using a tagline and your tagline for some reason had the edge of water was at 2 meters, or if you were on a bridge and the bridge stationing was not aligned with the edge of water, then you could add in an offset. But in general, most of the time, I would say our offset is 0. So you can enter that here, and then click Compute Stations. And then this will show you the location where you should sample. So the middle of each 20% of discharge is at this distance from wherever you started that transect. It's going to have this depth, and it's going to have this velocity. And so unfortunately for us is then we have to go to the tables and cross-reference those conditions with our ideal transit rate. Well, Hydrosedimentos gives you that information right there, which is amazing. So you're very lucky to have that program. So if the ADCP had GPS equipped, it will give you stationing information for those locations. So if you had a GPS, you could go specifically to those locations, set a mark or a waypoint, and you could go exactly to that location and do your sampling. So this is an example from Mike where what they do sometimes is instead of computing the EDI stations in the EDI program, is they will make a pass, a transect to determine the flow, and then they'll go back and they'll start the transect over again and look for the flow or the discharge to increment to that 10%, 30%, and so on location as they're going out to the channel. And this is good for big rivers where maybe it's hard to get right on that exact point and maintain station. So they're just incrementing to the point where they have that flow, and then they set a waypoint in their GPS equipment that's on the boat. Okay, so they mark those locations, and then they have those stored that every time they go back to the site, and if it's a similar flow condition, they can go right back to those same locations using the onboard GPS system on the boat. Okay, so I'm not going to go into the whole lot of the limitations, but it's certainly, we are not at the point that you all are with Hydrosedimentos. There's a lot that we learn from you, and we hope to improve our programs based on what you've done with your program and be able to expand our EDI program to be able to accommodate more types of instruments and types of measurements. and give you transit rate information would be very valuable. So it's time for lunch. So I think what we can do is, we can do questions after lunch, and then I've got an exercise that we'll do. So we'll do that right after.
Yeah, okay.
Does that work? Okay. Oh, that restaurant is fine.
Yeah?
Yeah,
Okay,
completely.
You can go to the steakhouse here, but you have more 30 minutes maybe in the interval for the lunch, maybe 1.5. Okay, it's up to you.
We could talk to Tim and Mike and see what they want to do. But
Could you ask
yeah,
them?
let me
Just
ask.
for give
Okay.
some
Okay.
instruction here for that.
Okay.
Pessoal, só um segundinho aqui, só pra gente, 2 segundinhos, só para eu resolver uma coisa aqui rapidinho, só para ver a questão do intervalo para o almoço.
Hey guys.
São 12 horas em ponto. Como a Molly vai continuar depois do almoço, a gente deixou perguntas para depois do almoço. Eu só resolver uma questão rapidinho com eles aqui. 2 segundinhos eu passo para vocês. Rapidinho aqui, só espera aí, 3 minutinhos. Oh.
We go to the same.
Yeah,
place,
okay. Ok. Então vamos fazer o intervalo, são 12 horas em ponto agora, né? A gente volta 1h da tarde, aí se alguém tiver alguma pergunta sobre a apresentação da Molly, faz nesse horário. Então a gente volta 1h. Bom almoço.
Recebeu e-mail da Ju com a nossa